What if everything you thought you knew about gravity was just the beginning of the story? We feel it every single day, the gentle tug that keeps our feet on the ground, the invisible hand that guides the moon in its orbit, the force that sculpts galaxies across the cosmos. For centuries, we've accepted gravity as one of the universe's fundamental building blocks, a force so familiar it seems almost mundane. But what if it's not fundamental at all? What if gravity, in all its cosmic grandeur, is merely a side effect, an echo rippling into our world from realms we can't see, touch, or even fully imagine? This isn't science fiction. It's one of the most provocative ideas emerging from the frontiers of theoretical physics, the possibility that gravity arises from hidden, forgotten dimensions, realms curled up and concealed within the very fabric of space and time, dimensions we haven't yet learned to chart or perceive. Think about that for a moment. The force that shapes the fate of stars and holds our reality together might be nothing more than a shadow, a glimpse into a deeper, richer cosmic architecture just beyond our current understanding. It's a concept that challenges not only how we see the universe but how we see ourselves within it. In this video, we're setting out on a journey to explore this breathtaking possibility. We'll dive into the theories that suggest gravity could be leaking into our world from these unseen dimensions, unpack the science that points toward their existence, and discover why this idea isn't just fascinating, it could fundamentally revolutionize physics as we know it. From the mind-bending mathematics of string theory to daring experiments hunting for traces of these hidden realms, we'll bridge the gap between established science and the speculative edges of human knowledge. So join me as we venture into the unknown, question the nature of reality itself, and uncover how the mysteries of gravity might ultimately lead us to a universe far stranger and more magnificent than we ever dreamed. Picture a quiet afternoon in 1687, a young Isaac Newton sitting beneath an apple tree, lost in thought. The story might be embellished by history, but the insight it represents is very real. An apple falls, and in that simple, everyday event, Newton saw a universal truth, a force that not only pulls fruit to the ground, but also holds the moon in its orbit around the Earth. He called it gravity, and he described it with a single, elegant law. Every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This was a monumental leap. For the first time, humanity had a mathematical framework that could predict the motion of planets and the fall of objects with stunning accuracy. Newton gave us a universe governed by predictable, clockwork mechanics, where gravity was a mysterious but consistent force acting instantly across vast, empty distances. Yet, even as Newton's laws reigned supreme for over 2 centuries, a quiet unease lingered among physicists. This concept of action at a distance, how could the sun, 93 million miles away, reach out across nothingness and pull the Earth? Newton himself was famously uncomfortable with this, writing, "I frame no hypotheses on the nature of this invisible force. It worked, but the how remained a profound mystery." The stage was set for a revolution, and it arrived in the form of a young patent clerk named Albert Einstein. Dissatisfied with the Newtonian picture, Einstein spent a decade grappling with this problem, and in 1915 he unveiled his masterpiece, the general theory of relativity. With it, he didn't just revise Newton's idea, he completely reinvented it. Einstein declared that gravity is not a force at all, not in the traditional sense. Instead, he proposed that mass and energy warp the very fabric of the universe, the 4-dimensional continuum of spacetime. Imagine spacetime as a taut, flexible rubber sheet. Place a heavy bowling ball in the center and it creates a deep dimple. Now roll a marble nearby. It will spiral inward, not because a force is pulling it, but because it is simply following the curved path created by the bowling ball's distortion. That's gravity. The Earth orbits the Sun because it is traveling along the curvature in spacetime that the Sun's immense mass creates. General relativity was a triumph. It predicted phenomena Newtonian physics could not, like the bending of starlight around the Sun, which was confirmed during a solar eclipse in 1919, catapulting Einstein to global fame. But for all its brilliance, Einstein's theory also left us with new, even deeper puzzles. One of the most glaring is the problem of gravity's incredible weakness. Think about it. A small refrigerator magnet can generate enough electromagnetic force to overcome the entire gravitational pull of the Earth and leap up to stick on the door. Gravity is astronomically weaker than the other fundamental forces, the electromagnetic force, the strong nuclear force that holds atoms together, and the weak nuclear force responsible for radioactive decay. Why, if gravity is the curvature of spacetime itself, why is its effect so feeble compared to these other interactions? Einstein spent the later years of his life consumed by this very question, searching for a way to unify gravity with electromagnetism into a single, coherent framework. He once mused, "I want to know how God created this world. I am not interested in this or that phenomenon. I want to know his thoughts, the rest are details." He sensed that a deeper, more fundamental reality was waiting to be discovered, one that could reconcile the immense power of the cosmos with the puzzling fragility of its gravitational glue. This historical journey from Newton's apple to Einstein's curved spacetime is not just a tale of scientific progress. It's a roadmap that points directly toward the next great frontier. The unanswered questions left by these giants are not failures but clues. The profound weakness of gravity acts like a cosmic signpost, hinting that our understanding is still incomplete, that we might be missing a crucial piece of the puzzle. That missing piece, many physicists now believe, could be hiding in plain sight, or rather, hidden from sight altogether, in the form of additional spatial dimensions beyond the three we experience. The very success of general relativity, for all its power, is what now forces us to look beyond it, to consider that the force we call gravity might not be fundamental, but a side effect, a shadow cast by realities playing out in realms we have yet to chart. So if Einstein's theory points to a deeper mystery with gravity's weakness, where do we go from here? This is where one of the most ambitious and mind-expanding ideas in modern physics enters the picture: string theory. For decades, physicists have struggled to marry Einstein's general relativity, which governs the immense scale of planets and galaxies, with quantum mechanics, the bizarre but incredibly accurate rules that dictate the behavior of the impossibly small. These two pillars of physics are brilliant on their own, but they speak completely different mathematical languages and fiercely resist being combined. This conflict suggests that both are, in a sense, incomplete, that a deeper, more fundamental theory must be waiting in the wings. String theory emerges as a prime candidate for that grand unified theory, but it comes with a truly extraordinary requirement. Our universe must have more than just the three dimensions of space and one of time that we're familiar with. The core idea of string theory is as elegant as it is strange. It proposes that the fundamental building blocks of the universe are not point-like particles, as we've long believed, but incredibly tiny, vibrating loops of energy, strings. Think of a violin string. Depending on how it vibrates, it can produce a wide range of different musical notes. In string theory, these vibrational patterns are everything. One specific vibration might correspond to an electron, another to a quark, and yet another to a photon, the particle of light. The properties of each particle, its mass, its charge, everything about it, are determined by how its string vibrates. This elegant concept naturally incorporates all the known particles and forces into a single framework, but there's a catch, and it's a big one. The mathematics of string theory only works if the universe has more dimensions than we can see. For the equations to be consistent and avoid absurdities like probabilities greater than 100%, the strings need more room to vibrate. Most versions of the theory require 10 or even 11 spatial dimensions to function properly. This immediately begs the question, if there are all these extra dimensions, where are they? Why don't we see them, walk through them, or experience them in any way? The answer lies in a process called compactification. Imagine an incredibly long, thin garden hose stretching off into the distance. From far away, it looks like a simple one-dimensional line. But if you were an ant crawling on that hose, you would quickly discover it's not a line at all. It has a second dimension, a circular cross-section that you can travel around. The dimension is there, but it's curled up or compactified on a scale so tiny that from a distance, it's completely invisible. Physicists propose that the extra dimensions required by string theory are curled up in a similar way, but at a scale so infinitesimally small we could never hope to perceive them directly. They are compactified into intricate, complex shapes known as Calabi-Yau manifolds, a name that sounds like science fiction, but represents a very serious mathematical reality. At every single point in the space we move through, these 6 or 7 additional dimensions are curled up into a fantastically tiny, complicated knot far smaller than an atom. The development of string theory has been driven by brilliant minds, but few are as central as physicist Ed Witten. In the 1990s, Witten made a monumental leap by demonstrating that the 5 different competing versions of string theory were not rivals at all, but merely different perspectives on a single, deeper, 11-dimensional framework he called M-theory. This was a unifying vision that brought the field together, suggesting that the underlying theory was more powerful and comprehensive than anyone had suspected. And crucially, one of the most compelling aspects of this entire framework is how seamlessly it incorporates gravity. In the vibrational patterns of the strings, one mode of vibration naturally describes a particle with exactly the right properties to be the graviton, the hypothetical quantum particle that would mediate the force of gravity. For the first time, gravity isn't forced into the theory. It emerges from it beautifully and inevitably. This offers a potential pathway to finally achieve the dream of a quantum theory of gravity, solving the central problem that has plagued physics for nearly a century. String theory, with its requirement for extra dimensions, doesn't just suggest that hidden realms might exist. It argues that they must exist for the universe to make mathematical sense, and in doing so, it might finally explain why the gravity we feel is merely a faint echo of a much richer multidimensional reality. So if these extra dimensions are curled up and hidden all around us, how could they possibly explain the single most baffling feature of gravity, its astonishing weakness? To grasp just how peculiar this is, consider a simple experiment you can do right now. Take a small refrigerator magnet and hold it near a metal surface. With a faint click, it leaps from your fingers and sticks firmly in place. In that tiny, everyday event, the magnet has just accomplished something truly incredible. The electromagnetic force generated by that little piece of material was powerful enough to overcome the gravitational pull of the entire planet Earth. That's not just a small difference in strength, it's a cosmic chasm. Physicists call this the hierarchy problem. Gravity is roughly 10 to the 36 times weaker than the electromagnetic force. That's a 1 followed by 36 zeros, a number so vast it defies any intuitive understanding. If the strength of electromagnetism were equivalent to the energy of a roaring hurricane, the strength of gravity would be less than a single breath of air. For decades, this staggering imbalance has been one of the most persistent and embarrassing puzzles in all of fundamental physics. Why would nature create a universe with such a wildly lopsided set of rules? One of the most compelling answers to emerge suggests that gravity isn't actually weak at all. Instead, its apparent feebleness in our world could be a powerful clue that it is spreading out or leaking into dimensions we cannot perceive. Imagine you're standing in the center of a vast, empty field during a light snowfall. The flakes drift down evenly, and you feel just a few of them land on your shoulders. Now picture that same snowfall happening in a dense forest. The flakes still fall from the sky with the same intensity, but now the branches and leaves of the trees above you catch most of them. Only a tiny fraction manages to filter all the way down to where you're standing. From your perspective on the forest floor, the snowfall seems incredibly weak and diluted, even though its true source is just as strong as it was in the open field. In this analogy, the open field is the full, higher-dimensional bulk of space, and the forest canopy represents our familiar three-dimensional universe, what physicists call a brane, short for membrane. Gravity, in its full strength, exists throughout the entire higher-dimensional space, but from our limited, three-dimensional perspective, trapped on our brane, we only experience the tiny trickle of gravitational influence that actually leaks through to us. The force isn't weak, our perception of it is simply incomplete. This revolutionary idea was given a rigorous mathematical form in the late 1990s by physicists Lisa Randall and Raman Sundram. They proposed a model where our universe is a three-dimensional brane adrift within a higher dimensional realm, often called the bulk. In their vision, the other fundamental forces, like electromagnetism and the nuclear forces, are like waves or particles that are stuck to the surface of our brane. They cannot leave it, which is why they appear so strong and undiluted to us. Gravity, however, is different. The graviton, the particle that mediates gravity, is not confined to our brane. It can travel freely through the entire higher dimensional bulk. As a result, its influence spreads out and becomes diluted across these extra dimensions. What we feel as gravity is just the faint, leftover portion of its full strength that happens to intersect with our little slice of reality. In some versions of these models, gravity could be just as potent as the other forces in the full higher dimensional space, but from our vantage point, it seems almost impossibly weak because most of its effect is happening somewhere else, in a realm we cannot access. This transforms the hierarchy problem from a confusing flaw in our theories into a potential Rosetta Stone for decoding the structure of the cosmos. The incredible weakness of gravity is no longer an arbitrary parameter that needs to be explained away. It becomes a direct, measurable consequence of the geometry of the universe itself. It is a clue, a cosmic signature left behind by the existence of these hidden dimensions. If this idea is correct, then every time we feel the weight of our own bodies or watch an apple fall from a tree, we are not just witnessing a fundamental force of nature. We are catching a glimpse, however faint, of the vast and hidden architecture of reality, an architecture that extends far beyond the limits of our ordinary perception. This realization primes us for the next logical step. If gravity is leaking in from these other realms, what exactly is the nature of the place we call home within this grander scheme? This radical vision of our universe as a membrane, or brane, floating within a much larger, higher-dimensional reality is known as brane cosmology, and it offers one of the most tangible ways to imagine how these hidden dimensions could actually function. To grasp this, picture our entire observable universe, every galaxy, every star, every person, not as an island in a three-dimensional void, but as a three-dimensional surface. This surface is the brain. Now, imagine this brain is not alone. It exists within an incomprehensibly vast higher dimensional space that physicists call the bulk. This is the true, full reality, and our brain is just one slice of it, like a single, impossibly thin slice of bread in a cosmic loaf. In most models, this bulk could contain not just our brain, but many others, each potentially hosting its own entire universe with its own unique laws of physics. What makes this idea so powerful is how it explains the bizarre segregation of forces. Think of two enormous parallel sheets of paper floating close to each other in the air. These are two separate brains. On one sheet, you can draw particles, electrons, quarks, photons. These particles are like ink. They are stuck to the surface of their own sheet. They cannot leap off into the empty space between the sheets. They are forever confined to their two-dimensional world. This is exactly how the standard particles and forces of our universe behave. The electromagnetic force, the strong and weak nuclear forces, they are bound to our brain. This is why they seem so potent and undiluted to us. Their influence cannot spread out into the higher dimensional bulk. They are concentrated entirely within our three-dimensional slice of reality. Gravity, however, plays by a completely different set of rules. In this brain world scenario, gravity is not confined. The graviton, the particle that carries the gravitational force, is like a tiny speck of dust that is not drawn in ink, but is instead a real object that can exist between the sheets. It can detach from one brain, travel through the bulk, and land on another. This means that while the other forces are trapped, gravity is free to leak out. This single, elegant idea provides a stunningly simple explanation for its weakness. The strength of gravity we feel isn't its full strength. It's just the fraction of gravitational influence that hasn't leaked away into the vastness of the bulk. The force isn't feeble, it's just that most of it is operating in a realm we cannot access. The work of theorists like Lisa Randall and Raman Sundram was pivotal in moving this from a speculative idea to a rigorous mathematical framework. Their warped geometry model, proposed in 1999, showed how a specific curvature of the extra dimension could naturally produce this huge gap in strength between gravity and the other forces, all without requiring any new, undiscovered particles or unnatural fine-tuning of numbers. It was a revelation that demonstrated how the geometry of space itself could be the sole architect of the laws we observe. This transforms our entire view of the cosmos. It suggests that what we have long considered to be the entire universe might be just one neighborhood in a far grander metropolis of realities. Other brains could be drifting mere millimeters away from us in an unseen dimension, each containing entire alternate universes, complete with their own stars, planets, and perhaps even life, all completely invisible and unreachable to us because every force that would allow us to see or touch them is locked to its own brain. The only thing that might bridge the gap is gravity, the faintest whisper from a world next door. This conceptual leap doesn't just solve a physics problem. It completely redefines our place in the cosmos and sets the stage for the ultimate question. If this is true, how could we ever hope to find evidence for a reality that exists literally all around us, yet remains forever beyond our sight? But if our universe is indeed a brain floating in a higher dimensional bulk, and gravity is free to move through it, what about the extra dimensions themselves? Where are they, and how could something so vast remain so completely hidden from us? The answer lies in one of the most elegant and ingenious concepts in all of theoretical physics: compactification. Imagine you're looking at a garden hose stretched across a vast lawn. From your vantage point, it appears to be a simple, one-dimensional line. An ant, however, crawling along that same hose, experiences a completely different reality. In addition to moving forward and backward along its length, the ant can also journey all the way around its circular circumference. That second dimension is always there, woven into the very fabric of the hose, but it is curled up or compactified on a scale so small that from a distance, it's utterly invisible to the naked eye. This is precisely how physicists propose the extra dimensions of string theory remain hidden. They are not vast, expansive realms we could sail a spaceship through. Instead, they are curled up into incredibly tiny, complex shapes at every single point in the three-dimensional space we inhabit. The most famous of these shapes are known as Calabi-Yau manifolds, named after the mathematicians who first described them. Picture, if you can, a shape of exquisite and mind-bending complexity, a six-dimensional object with holes and twists, a sort of multi-dimensional donut with a fantastically intricate structure. Now imagine that this intricate shape is not something you hold in your hand, but is instead the geometry of space itself at a scale a billion times smaller than an atom. At every point you can point to the tip of your finger, the air in front of you, the screen of your device. There exists not just the three dimensions we know, but six additional spatial dimensions, all curled up into this fantastically small Calabi-Yau space. This isn't just a mathematical curiosity. The geometry of these compactified dimensions is absolutely critical. It determines everything about the physics of our universe. Think of the strings of string theory vibrating in this higher dimensional space. The way they vibrate is constrained by the shape of the compact dimensions. Much like the note a violin string produces depends on the length and tension of the string. The specific vibrational patterns allowed by the Calabi-Yau manifold's geometry dictate the properties of the particles we see, their mass, their charge, and even which fundamental forces exist. A differently shaped manifold would produce a completely different set of physical laws, perhaps a universe with no electrons, or where gravity is repulsive. In this profound sense, the entire universe we experience, every law of physics, every particle, the very fact that we exist, might be a direct consequence of the hidden, geometric architecture of these unseen dimensions. Physicists and authors like Brian Greene have done monumental work in visualizing these incredibly abstract ideas for the public, using powerful analogies to help us grasp a reality that is fundamentally beyond human perception. He often compares it to the strings on a violin. You can have a string that vibrates in its fundamental mode, producing a deep note, or in a higher harmonic, producing a higher pitched note. In exactly the same way, a string vibrating in the compactified dimensions could manifest as an electron in one mode, or a quark in another. The geometry of the hidden dimensions is the instrument, and the music it plays is the symphony of particles that makes up our physical reality. Of course, a concept this extraordinary begs an obvious and pressing question. If these dimensions are everywhere, how could we ever hope to detect them? The challenge is one of scale and energy, because these dimensions are compactified to such an unimaginably tiny size. Directly observing them would require probing the fabric of spacetime at correspondingly tiny distances. According to the rules of quantum mechanics, to probe smaller distances, you need higher energies. We would need particle accelerators powerful enough to smash particles together with energies trillions of times greater than what the Large Hadron Collider can currently achieve. It's a sobering technological barrier, but it doesn't make the idea untestable. We might not see the dimensions directly, but we could detect their fingerprints, subtle effects on particle interactions, or slight deviations in the behavior of gravity at microscopic scales that whisper of a richer, more complex spatial reality just beneath the surface of our perception. To truly understand how gravity might be leaking into our world from these hidden dimensions, we need to introduce a key player in this cosmic drama, the graviton. In the standard model of particle physics, every fundamental force has a carrier particle, a messenger that conveys its influence. For electromagnetism, it's the photon. For the strong nuclear force, it's the gluon. The graviton is the hypothetical, yet to be discovered particle that would play that same role for gravity, acting as the quantum carrier of the gravitational force. According to the theory, every time an object attracts another through gravity, it's because a continuous exchange of these tiny, massless gravitons is happening between them. This particle-centric view is our best attempt to describe gravity using the same quantum rules that govern the other forces, and it's absolutely essential for any hope of unifying Einstein's general relativity with quantum mechanics. Now, when we place the graviton into a universe with extra dimensions, its story becomes far more fascinating. In the classic four-dimensional view of spacetime, a graviton emitted from a mass would spread its influence in all three spatial directions, and its strength would diminish with distance according to the familiar inverse square law, just like the light from a bulb appears dimmer the farther away you move. But if our universe is a brane floating in a higher dimensional bulk, the graviton's behavior changes dramatically. Instead of being confined to our three-dimensional slice of reality, it is free to propagate through the entire bulk into all of the extra dimensions. This means its influence isn't just spreading out in the three directions we know, it's also spreading out into these additional, hidden directions. From our perspective on the brane, this is like trying to fill a much larger, multidimensional container with the same amount of water. The depth of the water in our little corner of the container becomes much shallower. The graviton's power is diluted across a vastly greater volume of space, which is why its effect, which we perceive as gravity, appears so incredibly weak to us. But the weirdness doesn't stop there. Just as a guitar string can vibrate in different modes to produce a fundamental note and a series of harmonics, the compactified extra dimensions can force the graviton to exist in a spectrum of different vibrational states. These are known as Kaluza-Klein modes. The lightest mode would be the standard graviton we've been searching for, but there could be a whole tower of heavier, excited states, like echoes or resonances of the graviton at higher energies. If these heavier modes exist, they could have profound and potentially observable consequences. For instance, in particle colliders like the Large Hadron Collider, if enough energy is concentrated in a tiny space, it might be possible to briefly create these massive graviton modes. They would be incredibly short-lived, instantly disappearing back into the higher dimensional bulk, but their creation would be registered in the detectors as a dramatic event where energy seems to vanish from our brane entirely, providing a tantalizing indirect signature of their existence. The direct detection of a single, individual graviton, however, remains a monumental challenge that many physicists believe may be fundamentally impossible with any technology we can currently conceive. The problem is one of unimaginable weakness. Because gravity is so exceptionally feeble, the interaction cross-section, the likelihood of a graviton interacting with a particle in a detector, is vanishingly small. It's been compared to trying to detect the ripple from a single pebble dropped into a vast, stormy ocean. The signal is simply too weak to pick out from the background noise of the universe. This hasn't stopped researchers from thinking creatively, though. Some have proposed that the cumulative effect of countless gravitons, or the specific signatures of their heavier Kaluza-Klein cousins, could leave indirect marks on other phenomena. For example, precise observations of the cosmic microwave background, the afterglow of the Big Bang, or detailed studies of how gravitational waves propagate across the universe might reveal subtle inconsistencies that point toward graviton behavior and, by extension, the extra dimensions they call home. This relentless pursuit of the graviton is far more than an academic exercise. It represents the very heart of the quest for a complete theory of quantum gravity. Unifying the colossal, geometric world of general relativity with the probabilistic, particle-based world of quantum mechanics is the single greatest unsolved problem in fundamental physics. The graviton sits directly at this crossroads. If it exists, and if we can understand its properties, it would provide the crucial bridge, showing us how the smooth curvature of spacetime emerges from the frantic quantum dance of discrete particles. It would finally allow us to write a single set of equations that describes the universe from the smallest subatomic scales to the largest galactic clusters, revealing the hidden mechanisms that have been operating just beyond our sight all along. So how do we move from these mind-bending theories to tangible, testable science? How do we hunt for something that, by its very nature, might be hiding in the tiniest crevices of space-time or in realms completely beyond our perception? The answer lies at the forefront of experimental physics, where incredibly sensitive instruments and colossal machines are being deployed to catch even the faintest whisper of these hidden dimensions. One of the most powerful tools in this search is the Large Hadron Collider, the LHC, a 27-kilometer ring buried beneath the border of France and Switzerland. This monumental machine smashes protons together at velocities approaching the speed of light, recreating the searing conditions of the early universe and allowing us to probe reality at scales a billion times smaller than an atom. In the context of extra dimensions, physicists aren't necessarily looking for a new particle to appear in the detectors. Instead, they are looking for something far more peculiar: missing energy. Here's how it could work. According to some models, if extra dimensions exist, the gravitons produced in these high-energy collisions wouldn't stick around in our three-dimensional brane. They would immediately carry their energy away, escaping into the higher dimensional bulk. From the perspective of the scientists analyzing the collision debris, it would look as though energy and momentum have simply vanished into thin air, violating one of the most sacred laws of physics, the conservation of energy. This signature of missing energy is a prime target for LHC researchers. So far, no definitive signal has been found, but the hunt continues, with each new round of data collection pushing the boundaries of what we can rule out and where these dimensions might be hiding. But what if the extra dimensions aren't accessible to the immense energies of a particle collider? What if their signature is not in the realm of the extremely energetic, but the extremely small? This is where a different class of experiments comes into play, ones that probe the fundamental nature of gravity itself. For over 3 centuries, Newton's law of universal gravitation, the idea that the force between two objects weakens with the square of the distance between them, has held true. But if there are extra dimensions, this inverse square law might begin to break down at incredibly tiny distances. At scales comparable to the size of those compactified dimensions, gravity could start to behave differently, perhaps weakening faster or even following a different mathematical rule altogether as it begins to feel the full geometry of the higher dimensional space. To test this, scientists have designed exquisitely sensitive tabletop experiments. A premier example is the EART-WASH group at the University of Washington. They use a device called a torsion balance, which is essentially a modern, hyper-precise version of the apparatus used by Henry Cavendish in 1798 to first measure the gravitational constant. Their setup involves 2 rotating rings, each dotted with carefully machined holes, suspended incredibly close to a similar stationary ring. the gravitational attraction between these rings creates a tiny, measurable twist in the suspended system. By rotating the rings and monitoring this twist with laser beams at distances smaller than the width of a human hair, the team can search for any deviation from the predictions of Newtonian gravity. It's a breathtaking feat of engineering, searching for a new law of physics in the almost imperceptible tug between two pieces of metal in a vacuum chamber. The results from these painstaking experiments have so far been null. They have found no deviation from Newton's inverse square law down to distances of just a few micrometers. While this might sound like a failure in science, a null result is still a profoundly important result. It tells us what isn't true. It has effectively ruled out entire classes of models that predicted large extra dimensions would manifest at those accessible scales. But it hasn't killed the idea altogether. Far from it. These null results simply tell us that if extra dimensions are real, they are either even smaller than we've been able to probe, or they are warped in such a way that their effects are shunted to energy scales or distances that remain, for now, just beyond our grasp. The search is far from over. It's just becoming more refined. The challenge, then, is immense. We are trying to detect something that could be hidden across a vast landscape of possibilities, dimensions that could be a millimeter in size or a billion times smaller, dimensions that are flat or wildly curved. It's like searching for a single, specific grain of sand on all the beaches of the world without knowing what that grain looks like. Future experiments are already on the drawing board. Next-generation particle colliders, like the proposed future circular collider with a circumference of over 90 kilometers, would smash particles with even greater energy, probing even smaller distances. And advanced gravitational wave observatories, like the space-based LIS mission, could listen for the ripples of colossal cosmic events, searching for subtle distortions in the signals that might indicate gravitons leaking into extra dimensions as the waves travel across the universe. This practical, relentless pursuit transforms a captivating theoretical idea into a tangible scientific quest, building anticipation for the day when one of these experiments might finally catch a glimpse of the hidden architecture of our reality. Now, let's take this conversation to the most extreme environment the universe has to offer, the black hole. These cosmic monsters, where gravity becomes so overwhelming that not even light can escape, are the ultimate testing grounds for any theory of gravity. In our familiar four-dimensional universe, we picture a black hole as a profoundly simple object, a perfect, smooth sphere defined by its event horizon, the point of no return. But if our universe is actually woven from more dimensions, this classic image shatters. A black hole in a higher dimensional reality would not be a sphere. It would be an object of impossible complexity, its event horizon a multi-dimensional membrane with a topology we can scarcely imagine, shaped by the intricate curls and folds of the hidden dimensions it encompasses. This isn't just a change in appearance, it fundamentally alters how a black hole lives and dies. Stephen Hawking's revolutionary work showed us that black holes aren't completely black. Due to quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. The properties of this radiation, its temperature, its spectrum, are dictated by the black hole's gravity. In a higher dimensional universe, that gravity is stronger at small scales because it's not as diluted. A microscopic, higher dimensional black hole would therefore be hotter and would evaporate far more rapidly and violently than a four-dimensional one of the same mass. This presents a breathtaking possibility. If extra dimensions exist, the immensely powerful Large Hadron Collider might, for a fleeting fraction of a second, be able to concentrate enough energy to create a tiny, microscopic black hole right here on Earth. It would be a spectacular event, evaporating instantly in a burst of particles that would light up detectors like a cosmic fireworks display, providing the most direct and dramatic evidence imaginable for the reality of these hidden realms. This idea also ventures into one of the most perplexing puzzles in modern physics, the black hole information paradox. Hawking's calculations initially suggested that information about what fell into a black hole, whether it was a star, a book, or a collection of atoms, is irretrievably lost when the black hole evaporates. This violates a core tenet of quantum mechanics, which states that information must always be preserved. Leonard Susskind and others have spent decades wrestling with this paradox. Intriguingly, the existence of extra dimensions could offer a path to a solution. If our universe is a brane in a larger bulk, the information isn't necessarily destroyed. It might be encoded on the event horizon, as one theory suggests, or it could even be ejected into the higher dimensional bulk, preserved but utterly inaccessible to us in our confined three-dimensional world. The paradox forces us to question the very nature of reality, and the answer might lie in acknowledging that our view of a black hole has been hopelessly limited, seeing only its three-dimensional shadow while the true drama unfolds in a grander, multidimensional theater. Contemplating these cosmic implications completely transforms the black hole from a terrifying void into a luminous beacon. It is no longer just a grave for stars but a potential key, a natural laboratory where the deepest secrets of gravity and dimensionality are written in the language of radiation, topology, and evaporation. By studying the most violent and extreme gravitational phenomena in the cosmos, we might finally find the clues that lead us to a complete understanding of the quiet, subtle pull we feel every day here on Earth, forever connecting the infinite vastness of space with the infinitesimally small dimensions hidden within it. At the heart of modern physics lies a numerical embarrassment so profound it's known simply as the hierarchy problem. It's the staggering, seemingly arbitrary difference in strength between two fundamental scales of nature. On one hand, we have the electroweak scale, the energy at which electromagnetism and the weak nuclear force unify, around 246 giga-electronvolts. This is the energy realm of the known particles, the world we can probe with our most powerful colliders. On the other hand, there's the Planck scale, the energy at which gravity is expected to become as strong as the other forces, a colossal 10 to the 19 giga-electronvolts. The gap between them is a factor of a 1 with 17 zeros behind it, a number so immense it has no precedent or parallel in any other physical law. This isn't just a big number, it's a screaming anomaly. It suggests that the Higgs boson, which gives other particles their mass, would require an impossible amount of fine-tuning to remain at its relatively low mass, counterbalancing quantum fluctuations with a precision of 1 part in a million billion. To many physicists, this isn't just a puzzle, it's a sign that our understanding is missing a crucial piece. This is where the concept of extra dimensions moves from being a mathematical curiosity to a potential savior. The revolutionary idea, pioneered by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia de Valle in the late 1990s, is breathtakingly simple in its logic. What if the Planck scale isn't actually that high? What if the fundamental, true scale of gravity is not 10 to the 19 giga-electronvolts, but something much, much lower? Their proposal, known as the AD model after their initials, suggests that the immense value we measure for the Planck scale is not fundamental. Instead, it is an illusion, a consequence of gravity's ability to leak into large extra dimensions. In their vision, the true scale where quantum gravity becomes important could be as low as a tera-electronvolt, an energy range well within the reach of the Large Hadron Collider. Here's how this cosmic sleight of hand works. imagine gravity's strength is not diluted because the dimensions are small, but because they are surprisingly large. In this model, our universe is a three-dimensional brane, but the extra dimensions are not compactified into tiny Calabi-Yau shapes. They could be as large as a fraction of a millimeter. All the standard model particles and forces are stuck on our brane, so they only feel the three familiar dimensions of space. Gravity, however, feels the full spatial geometry. In a universe with n extra large dimensions, the gravitational force spreads out into this greater volume. The Planck scale we measure in our three-dimensional world is not the true fundamental scale. It is an effective scale derived from the true higher dimensional gravity scale and the size of these new dimensions. By choosing the size of these dimensions appropriately, the true gravity scale can be dramatically lowered. The mind-boggling hierarchy between the electroweak force and gravity simply evaporates, replaced by a natural consequence of the geometry of the cosmos. The beauty of this idea is that it doesn't just solve a theoretical problem with a hand wave, it makes a concrete, testable prediction. If the true quantum gravity scale is only a tera-electronvolt, then the LHC wouldn't just be looking for missing energy from gravitons, it could actually begin to probe the quantum realm of gravity itself. It might produce microscopic black holes or detect the heavy, resonant Kaluza-Klein modes of gravitons. This prospect sent a shockwave of excitement through the physics community because it transformed the search for extra dimensions from a purely theoretical exercise into an experimental race. While these specific signals have not yet been found, constraining these models has become a major driver of collider research. The hierarchy problem, once a source of deep philosophical unease, was suddenly recast as our most powerful guide, a beacon pointing directly toward experiments that could unveil the hidden structure of reality, proving that the most abstract mathematical ideas can have the most tangible physical consequences. But what if the very idea of gravity as a fundamental force, whether confined to a brane or leaking from a bulk, is itself an illusion? This brings us to one of the most profound and paradigm-shifting concepts in modern theoretical physics, the possibility that gravity is not fundamental at all. Instead, it may be an emergent phenomenon, a collective behavior that arises from the complex interactions of more basic quantum ingredients, much like the temperature and pressure of a gas emerge from the frantic motion of countless individual molecules. This radical perspective suggests that the force we feel holding us to the planet is not a primary building block of the universe but a secondary effect, a consequence of a deeper, more fundamental reality operating at the quantum level. At the heart of this emergent gravity idea is the bizarre quantum property known as entanglement. When two particles become entangled, their fates are inextricably linked. Measuring the state of one instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to defy our classical notions of locality and separation. Now, imagine this phenomenon not just for pairs of particles, but for vast, complex networks of quantum connections spanning the entire universe. A growing body of work pioneered by thinkers like Mark van Romsdonk suggests that spacetime itself, the very stage upon which gravity plays out, might be woven from this fabric of quantum entanglement. The gravitational force we attribute to the curvature of spacetime could, in fact, be a manifestation of these invisible quantum threads connecting everything. It's a breathtaking inversion. Gravity doesn't shape the universe. The universe's quantum connections give rise to the illusion of gravity. This view finds its most powerful expression in a groundbreaking discovery made by Argentine physicist Juan Maldacena in 1997. He proposed what is now known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This is a concrete mathematical duality, a kind of dictionary that translates a theory of gravity operating in a certain type of universe into a completely different theory that lives on that universe's boundary. The most famous example involves a hypothetical five-dimensional universe with a negative curvature, known as anti-de Sitter space. Maldassner showed that the physics of gravity within this five-dimensional bulk is perfectly equivalent to a four-dimensional quantum field theory operating on its boundary, a theory that contains no gravity at all. In this holographic principle, our familiar four-dimensional world of gravity could be a projection, a hologram encoded on a distant, lower-dimensional surface. To grasp this, think of the security hologram on your credit card. It appears as a full, three-dimensional image that you can look around with depth and perspective. Yet, all of that information is actually encoded on a flat, two-dimensional piece of foil. In an analogous way, Maldassner's work suggests that our four-dimensional universe, complete with the force of gravity and the curvature of spacetime, might be a holographic projection from a quantum theory that exists on a three-dimensional boundary. The gravity we experience is not the main event, it is a shadow, a consequence of the interactions described by that boundary theory. This provides a stunning new interpretation of those forgotten dimensions. They aren't just additional spatial directions, they are the scaffolding from which our entire reality, gravity included, emerges. The force that governs the motion of planets becomes a side effect of quantum information processing happening on the edge of our perceived reality. This philosophical shift is nothing short of revolutionary. For centuries, since the time of Newton, we have treated gravity as a primary agent, a fundamental player in the cosmic drama. The emergent gravity paradigm challenges this at its core, suggesting we've been watching the shadow play on the cave wall without understanding the puppeteers. It opens up electrifying new avenues for unification, proposing that the long-sought theory of quantum gravity might not be about quantizing spacetime itself, but about understanding how spacetime and gravity naturally arise from a quantum system that doesn't include them to begin with. It forces us to ask a deeply provocative question. If gravity can emerge from something more basic, what about the other forces? Could electromagnetism, the strong and weak nuclear forces, and even the particles of matter themselves also be emergent phenomena, all arising from a single, vast, interconnected quantum network? The search for the origin of gravity may ultimately lead us to the origin of everything. Our minds are exquisitely tuned to navigate a world of three spatial dimensions. We instinctively understand length, width, and depth. We can judge distances, catch a ball, and find our way through a crowded room without a second thought. But this very proficiency creates a profound barrier when we try to conceive of a fourth spatial dimension, let alone the 6 or 7 required by string theory. We are, in a sense, prisoners of our own perception, trying to imagine a reality for which we have no evolutionary context or sensory experience. This is the monumental challenge at the heart of this entire discussion. How do we visualize the invisible? How do we chart realms that, by their very nature, defy our innate sense of geometry? Fortunately, we are not left completely without tools. For well over a century, mathematicians and physicists have developed clever analogies and methods to circumvent the limitations of our three-dimensional brains. One of the most enduring and powerful tools is the concept of projection. Think of the humble shadow. A three-dimensional object like your hand casts a two-dimensional shadow on a wall. That shadow is a flattened, simplified representation of the original object. By the same logic, a four-dimensional object would cast a three-dimensional shadow into our world. This is the principle behind visualizing a tesseract or a four-dimensional hypercube. We cannot see the tesseract itself, but we can study its three-dimensional shadow. If you take a cube and drag it in a direction perpendicular to all three of its dimensions, a feat we can describe mathematically but not perform physically, you generate a tesseract. The shadow we can render looks like a smaller cube nestled inside a larger cube, with every corner of the inner cube connected to the corresponding corner of the outer cube. It's a strange, complex shape that hints at a richer geometry just beyond our grasp. This approach of using lower-dimensional analogues was brilliantly and famously explored in 1884 by Edwin Abbott in his novella Flatland, a romance of many dimensions. Abbott tells the story of a square living in a two-dimensional world, a flat plane where everything exists as lines and shapes. The square cannot conceive of height, just as we struggle with a fourth dimension. His worldview is shattered when a three-dimensional sphere visits him, passing through his plane and appearing first as a point that grows into a circle of varying size before shrinking back to a point and vanishing. To the square, this is pure magic, but to us, it's a simple object moving through a lower dimension. Flatland is more than a charming story. It's a profound thought experiment that forces us into the square's perspective. It makes us viscerally feel the limitations of our own perception and opens the door to the humbling possibility that we are the Flatlanders, oblivious to the higher dimensional realities that might be intersecting with our own. Moving from literature to modern technology, we now have even more powerful methods for peering into these abstract spaces. Advanced computer simulations and virtual reality allow researchers to create interactive models of higher dimensional objects and spaces. A mathematician can program the equations governing a Calabi-Yau manifold and then rotate it, slice it, and explore its properties in a simulated environment. While they are still looking at a three-dimensional projection on a two-dimensional screen, the ability to manipulate the object in real time provides an intuitive understanding that static images or equations alone cannot convey. Artists and filmmakers have also embraced this challenge, creating stunning visualizations that translate complex mathematical concepts into arresting imagery, from the folding landscapes in Interstellar to dedicated art installations that use light and sound to evoke the feeling of multidimensional space. This fusion of art and science is crucial because it engages our pattern recognition and spatial reasoning skills in new ways, building a bridge between abstract theory and tangible intuition. Ultimately, the drive to visualize these unseen dimensions is not merely an academic exercise. For researchers, developing an accurate intuitive feel for higher dimensional geometry is essential for generating new hypotheses and understanding the mathematical consequences of their theories. The shape of the compactified dimensions in string theory directly determines the laws of physics in our universe. So being able to mentally navigate these shapes is a key part of the theoretical toolkit. For the public, clear and compelling visualizations are the gateway to understanding these revolutionary ideas that are reshaping our concept of reality. They demystify the intimidating mathematics and make the profound implications accessible to everyone. This process of visualization, of striving to see the unseen, is a fundamental act of human creativity. It is how we push the boundaries of knowledge, transforming the impossible into the conceivable, and perhaps one day into the known. To truly chart these forgotten dimensions, we need the right set of tools, a precise and powerful language capable of describing realities we cannot see. That language is mathematics, specifically two profound disciplines, a differential geometry and topology. If we imagine the universe as a magnificent, multi-dimensional sculpture, differential geometry provides the tools to measure every curve and contour of its surface, while topology allows us to understand its fundamental shape, whether it's a sphere, a donut, or something far more complex. These aren't just abstract academic pursuits, they are the essential frameworks that allow theorists to build rigorous models of higher dimensional spaces and understand how gravity might weave through them. At the heart of this mathematical toolkit is the concept of a manifold. Think of the world you live on. The Earth is a sphere, but if you look at a small enough patch of ground, a city park for instance, it appears perfectly flat. A manifold is a mathematical space that has this same property. On a small enough scale, it looks and behaves like ordinary, flat Euclidean space, even if its overall global shape is wildly curved and complicated. The surface of a sphere is a two-dimensional manifold. The space around us is a three-dimensional manifold. The extra dimensions proposed by string theory are 6 or 7-dimensional manifolds, curled up into those intricate Calabi-Yau shapes. This idea allows physicists to work with these spaces using the familiar rules of calculus and geometry, just applied in more dimensions. Differential geometry gives us the vocabulary to describe the curvature of these manifolds. Bernhard Riemann, a brilliant 19th-century mathematician, was the pioneering architect of this field. He developed the mathematics to describe curvature in any number of dimensions using objects called tensors. The most important of these is the Riemann curvature tensor. You don't need to understand the complex math behind it, but you can think of it as a multi-dimensional GPS system. It tells you exactly how much a manifold is curved or warped at any single point, and crucially, how that curvature changes as you move through the space. For gravity, this is everything. In Einstein's general relativity, the Riemann tensor is what encodes the gravitational field. It mathematically represents the warping of spacetime by mass and energy. To describe gravity leaking into extra dimensions, physicists use this same mathematical machinery, but now applied to a higher dimensional manifold. The equations become more complex, but the principle remains. Matter tells spacetime how to curve, and the curvature of that multi-dimensional spacetime tells gravity how to behave. Then there's topology, which is often called rubber sheet geometry. A topologist is interested in the properties of a shape that remain unchanged no matter how much you stretch, twist, or bend it, as long as you don't tear it or glue parts of it together. A classic example is a coffee mug and a donut. To a topologist, these are the same shape because one can be smoothly deformed into the other. They both have exactly one hole. This is a profound distinction from geometry. A triangle and a square are geometrically different but topologically identical, while a sphere and a donut are geometrically similar in their smoothness but topologically different because one has a hole and the other does not. For string theory, the topology of the compactified dimensions is absolutely paramount. The number of holes in a Calabi-Yau manifold, for instance, determines key properties of our universe, like how many generations of particles we have. It's a staggering idea. The number of families of electrons and quarks might be a direct consequence of the number of holes in the invisible, six-dimensional geometry of space itself. The power of these mathematical frameworks is beautifully illustrated by a groundbreaking idea from a century ago. In 1919, a little-known German mathematician and physicist named Theodor Kaluza had a moment of sheer inspiration. He took Einstein's recently published equations of general relativity, which describe gravity in four-dimensional spacetime, and did something astonishingly simple. He wrote them out for a five-dimensional universe. When he did this, the equations didn't just describe gravity. Something miraculous happened. The additional components of the five-dimensional gravitational field perfectly arranged themselves into the equations for Maxwell's theory of electromagnetism. By simply adding an extra dimension, Kaluza had seemingly unified gravity and electromagnetism into a single, elegant geometric framework. It was as if the electromagnetic force was just a subtle side effect of gravity operating in a higher dimension. Of course, there was an immediate and obvious question: where is this fifth dimension? Kaluza's colleague, Klein, later proposed an answer. He suggested the dimension wasn't missing. It was compactified, curled up into a circle so tiny it was undetectable. This Kaluza-Klein theory, while ultimately not a complete description of nature, was a revolutionary proof of concept. It demonstrated the incredible power of differential geometry. By using its language, physicists could describe new forces not as separate entities, but as geometric features of a higher dimensional reality. This early work directly inspired the development of string theory decades later, providing the first tantalizing hint that all the forces of nature might one day be understood as vibrations in a space with more dimensions than we can see. These mathematical tools are the unsung heroes of theoretical physics, providing the rigorous foundation that allows us to explore the farthest reaches of possibility and perhaps one day to read the hidden blueprints of the cosmos. Imagine the thrill of discovery in 1919, when a young Albert Einstein was reshaping our understanding of gravity with his general theory of relativity. The scientific world was electrified, and yet one physicist saw something even more profound hidden within Einstein's equations. Theodore Kaluza, a mathematician working in relative obscurity, performed a breathtakingly simple act of mathematical daring. He took Einstein's complex field equations, which described the warping of four-dimensional spacetime, and rewrote them for a universe with not 4 but 5 dimensions. The result was nothing short of magical. The equations didn't just describe gravity. The additional mathematical terms that appeared from that fifth dimension perfectly and elegantly arranged themselves into the established equations for James Clerk Maxwell's theory of electromagnetism. In one stunning stroke, Kaluza had seemingly unified the two fundamental forces known at the time, gravity and electromagnetism, into a single, coherent framework. It was a monumental achievement, suggesting that the electromagnetic force might not be a separate entity at all, but merely a subtle geometric side effect of gravity playing out in a higher dimensional reality. But this brilliant insight immediately presented a profound and obvious puzzle. If there is a fifth dimension, where is it? Why can't we see it, move through it, or detect it in any way? This is where Klein entered the picture a few years later. Building on Kaluza's work, Klein proposed a revolutionary solution. The fifth dimension isn't missing, he argued, it is simply compactified. Imagine a drinking straw. From a distance, it looks like a one-dimensional line, but if you look closely, you see it has a second dimension, a circular cross-section curled up into a tiny loop. Klein suggested that the fifth dimension is curled up in exactly this way, but on a scale so inconceivably small, on the order of the Planck length, that it is completely invisible to all our instruments and senses. This elegant idea, now known as Kaluza-Klein theory, provided a complete and beautiful picture. Our four-dimensional universe is like the length of the straw, while the fifth dimension is the tiny, circular direction curled up at every single point in space. In this model, the different components of the five-dimensional gravitational field manifest in our four-dimensional world as both the familiar graviton and the photon, the particle of light that carries the electromagnetic force. For a time, it seemed like Kaluza and Klein had found the holy grail of physics, a unified field theory. Einstein himself was initially captivated by the idea, corresponding with Kaluza and seriously engaging with its implications. The theory was incredibly seductive in its geometric purity, suggesting that the entire universe could be understood as a consequence of the shape of space itself. However, this early enthusiasm eventually faded as the theory's significant limitations became apparent. The most glaring problem was the prediction of a new, massless scalar field, a theoretical particle that came out of the equations but had no counterpart in the real world. No experiment had ever detected such a thing, and it wasn't clear what its role would be. Furthermore, as quantum mechanics developed and new nuclear forces, the strong and weak forces, were discovered, the Kaluza-Klein framework seemed too simplistic. It could beautifully unify gravity and electromagnetism, but it had no obvious way to incorporate these new forces. It was a theory for a universe that was simpler than the one we actually inhabit, and so, by the mid-20th century, it had largely fallen out of favor, relegated to a fascinating historical footnote. Yet, the true legacy of Kaluza-Klein theory is not its failure, but its profound and enduring inspiration. It was the first serious, mathematically rigorous attempt to use higher dimensions to unify the forces of nature, and it planted a seed that would take decades to germinate. When string theory emerged in the latter part of the 20th century, physicists realized that its core requirement for extra dimensions was a direct descendant of Kaluza and Klein's original vision. String theory didn't need just one extra dimension. It needed 6 or 7, all compactified into those intricate Calabi-Yau manifolds. And just as a 5-dimensional gravity field in Kaluza-Klein theory could produce both gravity and electromagnetism in 4 dimensions, the vibrations of strings in a 10-dimensional universe could produce all the known forces and particles. The modern concept of branes, our universe, as a membrane in a higher dimensional bulk is also a direct evolution of the idea that some forces might be confined to a lower dimensional slice of reality. Contemporary physicists have even found ways to address the original shortcomings of the theory, that problematic massless scalar field predicted by Kaluza and Klein. In modern string theory, there are many such scalar fields called moduli, and they are thought to acquire mass through complex processes, effectively hiding them from view and solving the original observational conflict. The Kaluza-Klein idea was not wrong, it was merely incomplete. It provided the fundamental blueprint, the powerful insight that geometry could be the ultimate unifying principle. The story of this theory is a powerful testament to the iterative nature of scientific progress. A brilliant idea can lie dormant for years, waiting for new discoveries and new mathematics to provide the tools needed to complete it. Kaluza and Klein's pioneering work demonstrates that even ideas that seem to fail can become the essential foundation for future revolutions, proving that in the quest to understand the cosmos, no genuine insight is ever truly forgotten. The quest to unite Einstein's theory of gravity with the bizarre rules of quantum mechanics is the single greatest unsolved puzzle in all of physics, and the question of extra dimensions sits right at its heart. This isn't a single, unified effort. It's more like a grand, multi-front exploration with several brilliant teams trying to summit the same mountain from completely different sides. Each approach has its own unique tools, its own guiding philosophy, and its own perspective on whether those forgotten dimensions are a necessary part of the solution or an unnecessary complication. String theory, as we've explored, is perhaps the most famous of these paths, and it places extra dimensions at the very core of its identity. The theory's mathematical consistency absolutely depends on them. Without those additional spatial directions for the strings to vibrate in, the equations break down, producing physical impossibilities like probabilities that add up to more than 100%. This need for anomaly cancellation, a mathematical requirement that all these quantum probabilities work out correctly, is what forces string theory into 10 or 11 dimensions. It's not a choice, it's a fundamental requirement for the theory to even make logical sense. In this framework, gravity is seamlessly incorporated as just one particular vibration of a closed string, the graviton elegantly weaving it into the quantum tapestry alongside all the other particles and forces. But string theory is far from the only game in town. Other prominent approaches take a very different view. Loop quantum gravity, for instance, is a fiercely minimalist contender. It doesn't seek to unify all forces. Its sole mission is to quantize spacetime itself, to describe its fabric as being made of discrete, tiny loops woven into a network. Crucially, loop quantum gravity does its work strictly within the familiar 4 dimensions of spacetime. It has no need for, and makes no prediction of, any extra dimensions. Its focus is on the granular quantum structure of the spacetime we already know and experience. Another fascinating approach, called causal dynamical triangulation, builds spacetime from the ground up by connecting tiny, simple geometric pieces according to specific rules. In computer simulations of this model, a 4-dimensional universe naturally emerges from the chaos, again without any prior assumption of hidden dimensions. These theories demonstrate that a theory of quantum gravity is conceptually possible without invoking extra dimensions at all. This divergence of views creates a fascinating intellectual landscape. We have string theory, which requires extra dimensions for its very survival, and other theories that see them as entirely superfluous. This isn't a weakness of science, it's a sign of its vitality, showing that we are exploring the problem from every conceivable angle. Yet, even with this competition, string theory's dimensional approach remains compelling for many because of its unique ability to naturally incorporate gravity alongside the other forces. It doesn't treat gravity as a separate problem to be solved, but as an integral part of a unified whole. However, this incredible strength of string theory also leads to its most famous philosophical challenge, the landscape problem. Because the geometry of the compactified dimensions, the specific shape of the Calabi-Yau manifolds determines the laws of physics in our observable universe, and because mathematics allows for a truly staggering number of possible shapes, string theory doesn't predict one unique universe. It predicts a vast multiverse of possibilities, often estimated at 10 to the 500 or more different potential universes, each with its own distinct physical constants, particles, and forces. This is the string theory landscape, an immense, dizzying array of possible vacuum states, of which our universe, with its specific particle masses and force strengths, is just one tiny island. This landscape problem is deeply intertwined with the nature of those extra dimensions. The specific way they are curled up and stabilized doesn't just predict extra dimensions, it predicts everything. The fact that we seem to live in a universe that is hospitable to life with the right balance of forces for atoms, stars, and planets to form might not be a fundamental law, but simply a consequence of our particular location in this cosmic landscape. For some, this is a Copernican-level blow, suggesting our physical laws are not special or unique. For others, it's a powerful explanation for the puzzling fine-tuning we observe, a form of natural selection on a cosmic scale. The extra dimensions are no longer just a mathematical trick. They become the very source of cosmic diversity, the hidden mechanism that allows for a multitude of physical realities, forever cementing their role as one of the most profound and provocative ideas in our search for a complete theory of everything. In September 2015, a revolution in astronomy quietly unfolded when the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded a faint chirp that had traveled across the cosmos for 1.3 billion years. This was the sound of two black holes colliding, an event so cataclysmic it sent ripples through the very fabric of spacetime itself, gravitational waves. Einstein predicted these ripples a century ago, but their direct detection was a triumph of human ingenuity, confirming one of the last unverified aspects of his general theory of relativity. It opened an entirely new window on the universe, allowing us to hear the collisions of black holes and neutron stars. But this breakthrough might be far more profound than we initially realized. These spacetime ripples could be much more than just messengers of cosmic catastrophes. They might be the most sensitive probes we have for detecting the hidden architecture of reality, those forgotten extra dimensions. According to Einstein's four-dimensional general relativity, gravitational waves have very specific properties. They travel at the speed of light, and they can only vibrate in two fundamental patterns or polarizations known as plus and cross. Think of these like the way a ripple on a pond might distort a floating ring, stretching it in one direction and then compressing it in another. Any deviation from this behavior would be a clear sign that Einstein's theory, while incredibly successful, is not the final word. This is where the possibility of extra dimensions creates a tantalizing opportunity. If our universe is embedded in a higher dimensional bulk, these gravitational waves would not be confined to our four-dimensional brain. As they propagate across the universe, some of their energy could literally leak out into these additional spatial dimensions. You can understand this effect with a simple analogy from everyday life. Imagine you're in a room and you hear a faint sound coming from the other side of a thick, solid wall. The wall absorbs and reflects most of the sound's energy, so what you hear is a diluted, muffled version of the original. Now replace the wall with a porous screen, and much more of the sound passes through, making it louder and clearer on your side. In this scenario, the gravitational waves are the sound. The higher dimensional bulk is the space on the other side of the screen. If there are no extra dimensions, the screen is solid, the waves travel entirely through our spacetime, and we detect them at full strength. But if extra dimensions exist, the screen becomes porous. Some of the wave's energy leaks through into the bulk, meaning the signal that arrives at our detectors would be weaker or attenuated than what standard four-dimensional physics would predict. For a collision happening at a fixed distance, we would receive a quieter signal than expected. This attenuation isn't the only potential fingerprint. The very way the waves travel could be altered. In some models, the leakage into extra dimensions could cause gravitational waves to effectively travel a longer, multi-dimensional path. This might make them appear to move slightly slower than the speed of light, another direct violation of pure general relativity. Furthermore, the existence of additional spatial dimensions could introduce entirely new, exotic polarization modes for the waves, ways for spacetime to ripple that are simply impossible in a strictly four-dimensional universe. Detecting any of these anomalies, an unexpectedly weak signal, a slight delay compared to light, or a strange polarization, would be like finding a cosmic signature, a direct piece of evidence that gravitational waves are interacting with a reality larger than our own. The challenge, of course, is that these effects are expected to be incredibly subtle. The first few dozen black hole mergers detected by LIGO and its European counterpart, Virgo, have so far shown no clear signs of extra dimensions. The waves have arrived on time and with the expected strength, consistent with Einstein's four-dimensional universe. But this doesn't rule the idea out. It simply tells us that if dimensions are there, they are either very small or configured in a way that makes their effects minimal for the events we've observed so far. The real promise lies with the next generation of observatories, space-based detectors like LISA. The Laser Interferometer Space Antenna will be able to listen for gravitational waves from truly enormous sources, like the mergers of supermassive black holes at the centers of galaxies. These waves would have been traveling for millions, even billions of years. Over such vast cosmic distances, Even a tiny amount of leakage into extra dimensions would have a cumulative effect, potentially creating a detectable dimming of the signal by the time it reaches us. This transforms gravitational wave astronomy from a spectacular confirmation of Einstein's theory into a potential hunting ground for physics beyond Einstein. Every chirp and thump from the dark reaches of space is now a data point that could contain hidden clues. As our detectors become more sensitive and our catalog of events grows into the thousands, we will be able to perform exquisitely precise tests. We will be able to compare the strength of waves from similar events at different distances, searching for that telltale sign of energy loss. We will be able to measure their speed with unprecedented accuracy and analyze their polarization with fine detail. We are no longer just listening to the symphony of the cosmos. We are analyzing the acoustics of the concert hall itself, searching for echoes that suggest the hall is far, far larger than we can see, with hidden balconies and chambers extending into realms beyond our perception. The gentle ripples that momentarily stretch our planet by less than the width of an atomic nucleus may be carrying the deepest secrets of the universe's true shape. When we look up at the night sky, we are witnessing a grand cosmic deception. The stars, the galaxies, the vast expanse of the cosmos, everything we can see with our most powerful telescopes, accounts for less than 5% of the universe's total content. The overwhelming majority, the other 95%, is completely invisible to us. We know it's there only through its gravitational effects. We call this hidden majority dark matter and dark energy, and they represent the single greatest unsolved mystery in all of modern cosmology. But what if these aren't separate, exotic substances? What if they are not things at all, but rather profound side effects, ghostly signatures of gravity spilling over from those forgotten dimensions we've been exploring? Let's start with dark matter. We observe that galaxies rotate at such tremendous speeds that they should fly apart. The visible matter within them, the stars and gas, simply doesn't provide enough gravitational glue to hold them together. Something else, something that doesn't emit or absorb light, must be providing the extra gravity. This invisible something is dark matter. For decades, the leading hypothesis has been that it's made of some unknown, slow-moving particle that rarely interacts with normal matter. But despite extensive searches, not a single one of these hypothetical particles has been found. This persistent failure has led some physicists to consider a far more radical idea. Perhaps dark matter isn't a particle in our universe at all. Perhaps the gravity we attribute to an invisible substance within our galaxy is actually the gravitational pull of ordinary matter residing on a separate brane, a parallel universe floating extremely close to ours in a higher dimensional bulk. Imagine two sheets of paper suspended mere millimeters apart in the air. You are a tiny ant living on one sheet. You can only perceive your own two-dimensional world. On the other sheet, another colony of ants is going about its business. You cannot see them, hear them, or touch them because all the forces that would allow that interaction, light, electromagnetism, are confined to their own sheet. But gravity, as we've established, can leak between the sheets. So when you, the ant on your brain, measure the gravity holding your galaxy together, you would feel not only the pull from the stars on your own sheet, but also the gravitational tug from all the stars, planets, and matter on the neighboring brane. From your perspective, this extra pull would seem to come from an invisible, mysterious source of mass permeating your universe. You would call it dark matter, but it would actually just be ordinary matter, shining brightly on a world right next door, forever hidden from your view. This is not just wild speculation. Physicists like Lisa Randall have developed sophisticated mathematical models based on this very premise. In her warped geometry model, our universe and a dark universe exist on separate branes within a 5-dimensional bulk. The gravity from the matter on that other brane could perfectly account for the missing mass we observe in our galactic rotation curves. This idea is breathtaking because it offers an elegant solution without requiring us to invent an entirely new, undetectable type of particle. The matter is there, it's just located in a dimension we cannot access. Then there is the even more perplexing mystery of dark energy. In the late 1990s, astronomers made the shocking discovery that the expansion of the universe is not slowing down due to gravity, as everyone expected, but is actually accelerating. Something is forcing space itself to stretch apart at an ever-increasing rate. This repulsive force, which makes up about 70% of the universe, was dubbed dark energy. Its nature is arguably the most profound puzzle in physics. Once again, extra dimensions might hold a key. What if this accelerating expansion isn't being driven by a mysterious energy field within our universe, but is instead a consequence of the very fabric of higher dimensional space evolving over time? The compactified dimensions of string theory are not necessarily static. Their size and shape could be dynamic, changing as the universe ages. As these hidden dimensions evolve, perhaps slowly expanding or contracting, they could exert a pressure on our observable 3-dimensional brane. This pressure from the higher dimensional geometry would manifest within our universe as a constant, pervasive force pushing everything apart. From our limited perspective, it would look exactly like dark energy. Furthermore, the specific value of the cosmological constant, the number that measures the strength of dark energy, could be determined by the particular way these dimensions are stabilized. Instead of being an arbitrary, finely tuned number, it would be a natural outcome of the multidimensional landscape we inhabit. Of course, these are extraordinarily difficult ideas to test. How do you look for a parallel universe or measure the evolution of a dimension curled up into a space a billion times smaller than an atom? The challenges are immense but not insurmountable. If dark matter is gravity from a nearby brane, there might be subtle differences in how it clumps and behaves compared to the standard particle dark matter model. Ultra-precise maps of the dark matter distribution in galaxies, which next-generation telescopes like the Vera Rubin Observatory will provide, could reveal these tiny discrepancies. For dark energy, if its origin is tied to the dynamics of extra dimensions, the acceleration rate of the universe might not be perfectly constant over billions of years. By measuring the expansion history of the cosmos with extreme precision, we might detect a drift in the strength of dark energy, a whisper of the unseen dimensions breathing and shifting behind the curtain of our reality. This bold hypothesis does more than just offer alternative explanations for two cosmic enigmas. It fundamentally reframes our search for understanding. Dark matter and dark energy may not be mysterious, dark things we need to find, but rather the clearest gravitational footprints of a larger, multidimensional reality. They could be the most dramatic evidence that our universe is not a lonely island, but one neighborhood in a far grander cosmic metropolis whose full dimensions and inhabitants remain, for now, just beyond the edge of our perception. This idea that our universe's specific physical laws might not be fundamental, but simply the only ones that allow for our existence, is known as the anthropic principle. First coined by astrophysicist Brandon Carter in 1974, the principle suggests that any observations we make about the universe must be compatible with the fact that we, as conscious observers, are here to make them. It's a statement that seems almost obvious, but its implications for physics are nothing short of revolutionary. When we apply this reasoning to the number of spatial dimensions, a fascinating possibility emerges. We don't perceive 7 or 10 spatial dimensions not because they don't exist, but because complex structures like atoms, planets, and people can only form in a universe with exactly 3. To understand why, we need to think about how forces behave in different dimensions. The stability of an atom, for instance, depends critically on the way the electromagnetic force behaves. In our 3-dimensional world, the force between an electron and a proton follows an inverse square law, creating stable, well-defined orbits that allow atoms to form. But if we lived in a universe with 4 or more large spatial dimensions, the force of electromagnetism would diminish much more rapidly with distance. In such a world, electrons couldn't maintain stable orbits around a nucleus. They would either spiral inward or drift away, making the formation of any complex matter impossible. Similarly, the very fabric of spacetime and the nature of gravity become wildly unstable in higher dimensional scenarios. The intricate dance that allows planets to orbit stars and galaxies to form relies on the specific, predictable curvature of 3 spatial dimensions. In a cosmos with more large dimensions, the gravitational interactions would be so chaotic that orderly solar systems could never coalesce. The 3 dimensions we experience might be the only possible configuration that allows for the long-term stability necessary for stars to shine, planets to cool, and life to eventually evolve. This line of thinking leads us directly to the concept of the multiverse and a form of cosmic natural selection. Pioneered by thinkers like Leonard Susskind, this view suggests that our universe, with its 3 spatial dimensions and 1 time dimension, is not unique. It could be just one bubble in a vast, perhaps infinite, foam of universes, each with its own random number of dimensions, its own laws of physics, and its own fundamental constants. In this grand cosmic landscape, the vast majority of these universes would be stillborn. They might have too many dimensions, leading to forces too weak to form atoms, or too few dimensions, creating a reality too simple and cramped to allow for any complexity at all. These universes would be empty, barren, and lifeless. Our universe isn't special because it was designed for us. We exist in this one simply because it's one of the exceedingly rare universes whose dimensional architecture is stable and complex enough to permit our existence. We are a product of our environment, and we can only observe an environment that allows for products like us. This introduces a profound, almost Darwinian twist to our understanding of reality. The dimensionality of our universe isn't a necessary truth. It could be a historical accident, a random roll of the cosmic dice that happened to come up with a winning combination for complexity. Those forgotten dimensions we've been exploring throughout this video might not just be hidden, they might be, for all practical purposes, uninhabitable. They could represent the countless failed experiments of the cosmos, the lawless and unstable realms where physics simply doesn't allow for the emergence of anything we would recognize as order or life. This perspective doesn't diminish our quest to find them. In fact, it makes it even more compelling. Charting these dimensions would be like an archaeologist uncovering the bones of extinct species. It would give us a glimpse into the broader and often hostile conditions of the multiverse, helping us understand not just how our universe works, but why it is the way it is at all. It transforms a question of physics into a question of existence itself, forever linking the number of dimensions we see to the fact that we are here to see them. The search for these hidden dimensions is not a lack of imagination or effort. It is a battle against the fundamental limits of our technology and the sheer scale of the unknown. We are, in a very real sense, trying to detect the undetectable with tools that are only just being conceived. The primary challenge is one of energy and scale. If these extra dimensions are compactified into incredibly tiny spaces, as string theory often suggests, then probing them requires us to concentrate an immense amount of energy into a correspondingly minuscule volume. Think of it like trying to discern the intricate pattern on a coin by throwing grains of sand at it from 100 yards away. Your sand simply isn't a fine enough probe to reveal the details. For dimensions curled up at the Planck scale, around 10 to the minus 35 meters, the energy required to probe them would be a staggering 10 to the 19 giga-electronvolts. To put that in perspective, the Large Hadron Collider, the most powerful particle smasher ever built, operates at energies of around 13,000 giga-electronvolts. We are off by a factor of 1,000,000 billion. It's the difference between a firecracker and a supernova. This isn't a limitation of will, it's a limitation of known physics and engineering, a barrier so high that it may require technologies we can't yet envision. This is why the null results from the LHC, while disappointing to some, are far from a death knell for these ideas. The collider has been searching for signs of extra dimensions by looking for missing energy, events where gravitons might carry energy away into the bulk, or for the telltale production of microscopic black holes that would instantly evaporate. So far, it hasn't found them, but this only tells us that if extra dimensions are real, they are either smaller or configured in a way that puts their effects beyond the current reach of our machines. It has ruled out a specific set of possibilities, which is how science progresses by narrowing the field of where to look next. This has only fueled the ambition to build bigger and more powerful instruments. The proposed future circular collider, a mind-boggling 90-kilometer ring that would dwarf the LHC, is one such vision. By colliding particles at energies nearly 10 times greater, it would probe distances a fraction of the size, potentially bringing a whole new realm of extra-dimensional possibilities within our grasp. These projects are decades-long, multi-billion-dollar endeavors, a testament to our species' deep commitment to answering these profound questions, no matter how long it takes. But what if the key isn't just brute force? What if we can find clever, indirect ways to sense these dimensions? This is where precision experiments and astrophysical observations come into play. On Earth, exquisitely sensitive tabletop experiments are pushing the boundaries of how we measure gravity itself. Projects like the Earth Wash Group use devices called torsion balances to test Newton's inverse square law of gravity at distances smaller than the width of a human hair. The idea is simple yet profound. If there are large extra dimensions, even ones a fraction of a millimeter in size, gravity should begin to deviate from its classic behavior at those tiny scales, pulling just a little harder as it feels the full geometry of a higher dimensional space. So far, these experiments have found space to be smooth and four-dimensional down to about 1 micrometer, another null result, but again, one that carves away another chunk of possibility and tells us exactly where not to look. Beyond our planet, the cosmos itself offers a natural laboratory of unimaginable power. Neutron stars, the ultra-dense corpses of dead suns, possess gravitational fields so intense they warp spacetime to its absolute limit. By carefully observing the behavior of matter falling onto these stars or the precise timing of pulsar rotations, astronomers can look for subtle anomalies that might betray the influence of extra dimensions on gravity's strength. Even more dramatic are ultra-high-energy cosmic rays, particles that streak across the universe with energies far beyond what any human-built collider can produce. When these cosmic projectiles smash into the Earth's atmosphere, they create showers of secondary particles. Some theories suggest that if extra dimensions exist and lower the true energy scale of gravity, these ultra-high-energy collisions might produce not showers but tiny, evaporating black holes. While we haven't seen convincing evidence of this yet, it represents a beautiful synergy between frontier theory and cosmic observation, using the universe itself as the ultimate particle accelerator. This realistic assessment tempers the thrilling theoretical possibilities with a necessary dose of scientific caution. The journey to chart the forgotten dimensions is a marathon, not a sprint. It is a story of brilliant ideas constantly running up against the hard wall of experimental reality, forcing theorists to refine their models and engineers to innovate beyond the impossible. Each negative result, each experiment that finds nothing out of the ordinary, is not a failure. It is a victory for the scientific process, a step forward that clears away the underbrush and shows us the path ahead with greater clarity. The evidence remains elusive not because the ideas are fanciful, but because the universe has hidden its deepest secrets exceptionally well. This ongoing challenge is what motivates a continuous cycle of innovation in detector design, data analysis, and pure mathematical creativity, a global effort driven by the unwavering belief that something incredible is waiting just beyond our current reach to be known. This journey into the nature of gravity and the cosmos forces us to confront a question that has haunted philosophers for millennia. What is the true nature of reality? For centuries, since the dawn of the scientific revolution, we have operated on a core principle of empiricism, the belief that knowledge comes primarily from sensory experience, from what we can see, touch, and measure. But what if our senses, and even our most powerful instruments, are fundamentally limited? The possibility that gravity is not a fundamental force but a mere echo from dimensions we cannot access delivers a profound challenge to this worldview. It suggests that the universe we perceive is not the entirety of reality, but merely a slice of it, a partial view filtered through the narrow keyhole of our three-dimensional perception. We are like sailors on a vast ocean, aware only of the surface waves and oblivious to the immense, teeming world of currents and life hidden in the depths below. This concept finds a powerful and ancient echo in Plato's allegory of the cave. In that famous thought experiment, prisoners are chained from birth inside a dark cave, forced to stare at a wall. Behind them, a fire casts shadows of objects passing by, and these shadows are the only reality the prisoners have ever known. They give names to the shadows, study their movements, and believe they understand the world completely. Then, one prisoner is freed and stumbles out of the cave into the blinding sunlight. He sees the real objects that were only ever projected as shadows, and he understands the profound poverty of his former existence. When he returns to the cave to tell the others, they dismiss him as a madman. The parallel to our modern scientific quest is striking. The force of gravity, as we experience it in our daily lives, could be the shadow on the wall. The true reality, the complex, multidimensional dance of strings and branes and gravitons, is the world outside the cave, bathed in a light our eyes are not yet built to see. We are the prisoners, meticulously measuring the shadows and believing we have grasped the full picture, while a deeper, richer truth remains just out of sight. This shift in perspective has dramatic implications for the philosophy of science itself. The work of Thomas Kuhn, a historian and philosopher of science, becomes incredibly relevant here. Kuhn argued that scientific progress does not always happen in a slow, steady, cumulative way. Instead, it often occurs through violent revolutions he called paradigm shifts. A paradigm is the entire constellation of beliefs, values, and techniques that a scientific community shares. It's the rulebook for how to do science at a given time. For centuries, the Newtonian and then the Einsteinian view of gravity formed a powerful paradigm. But when anomalies arise, persistent puzzles like the hierarchy problem that cannot be solved within the existing framework, a crisis occurs. This crisis can lead to a revolution where the old paradigm is overthrown and replaced by a new one. Accepting the existence of extra dimensions would represent one of the most profound paradigm shifts in human history. It wouldn't just add a new chapter to our physics textbooks, it would force us to rewrite the entire book from a completely different perspective, fundamentally altering our understanding of space, time, and the very fabric of existence. Such a revelation would force a deep and necessary humility upon us. It confronts us with the stark limits of human knowledge and perception. We have evolved to survive in a world of medium-sized objects moving at medium speeds, and our cognitive tools are exquisitely tuned for that purpose. But they may be hopelessly inadequate for comprehending the ultimate nature of reality. The quest to understand these hidden dimensions is not just a technical challenge for physicists. It is a fundamental human endeavor to break free from our cognitive cave. It asks us to consider that what we call reality might be a user interface, a simplified, practical dashboard that allows us to navigate the world, while the underlying code, written in the language of higher dimensional geometry, remains hidden from view. This isn't a call to abandon science, but rather to embrace a more expansive and humble form of it, one that acknowledges the possibility of realities beyond our current perception and has the courage to develop the new mathematics and new concepts needed to chart them. In doing so, we don't diminish our place in the cosmos. We expand it, recognizing that our ability to even ask these questions is a remarkable step in the universe's long journey toward understanding itself. Long before physicists were scribbling equations for Calabi-Yau manifolds, storytellers were already voyaging into the unseen realms beyond our own. Science fiction has always served as a powerful sandbox for the human imagination, a space where we can play with the most profound questions about reality, and the concept of extra dimensions has been one of its most fertile playgrounds. This dialogue between scientific speculation and artistic vision is far from one-sided. It's a vibrant, two-way street where ideas are borrowed, adapted, and sometimes even prophesied. The journey begins not with complex mathematics, but with a Victorian inventor hurtling through time. H.G. Wells' seminal 1895 novel, The Time Machine, introduced a radical idea to the public consciousness. That time could be treated as a dimension, just like length, width, and depth. While Wells' fourth dimension was temporal, not spatial, the cultural impact was seismic. It forced readers to conceptually break free from a static, three-dimensional world and consider the universe as a four-dimensional continuum, a block of spacetime where past, present, and future might all exist simultaneously. This was a crucial first step, preparing the cultural ground for the even stranger ideas to come. As the 20th century progressed, the fictional portrayal of dimensions grew more sophisticated and began to intertwine with emerging scientific thought. A pivotal moment arrived with Madeleine L'Engle's 1962 classic, A Wrinkle in Time. In it, she popularized the concept of a tesseract, a term borrowed from geometry, as a means of instantaneous travel across vast cosmic distances. Her characters don't fly through space, they wrinkle it, folding the fabric of the universe to bring two distant points together. This is a stunningly accurate metaphor for a wormhole, a hypothetical feature of spacetime predicted by Einstein's equations that could act as a shortcut through the cosmos. L'Engle's tesseract wasn't just a magical device, it was a literary embodiment of a genuine theoretical possibility, and it introduced an entire generation to the mind-bending idea that higher geometry could be the key to navigating the stars. Of course, science fiction often takes creative liberties to serve its narrative, and these departures from strict scientific accuracy are just as important as the accurate inspirations. When we see a hero in a movie visually navigating a shimmering, chaotic higher dimensional space, as in Interstellar's famous tesseract sequence, we are witnessing a necessary compromise. We are three-dimensional beings trying to visualize a five-dimensional bulk, and our brains need a visual shorthand, a user interface for the unimaginable. Christopher Nolan's film, developed in consultation with physicist Kip Thorne, is a masterclass in this balance. It presents one of the most realistic depictions of a wormhole and a black hole ever put to screen, with the computer-generated imagery for Gargantua leading to genuine scientific papers on gravitational lensing. Yet the film's climax, where Cooper floats in a library like Tesseract behind his daughter's bookshelf, is a brilliant piece of poetic license. It translates the abstract, non-linear nature of higher dimensional perception into a relatable, emotional language we can all understand, even if a pure physicist might quibble with the specifics. This interplay between fact and fiction is not merely for entertainment. It has a tangible, real-world impact on the scientific endeavor itself. The captivating ideas presented in stories can ignite a lifelong passion for discovery. Many practicing physicists and mathematicians today cite early exposure to works by authors like Isaac Asimov, Arthur C. Clarke, or Carl Sagan as the initial spark that led them to their careers. These narratives make the cold, abstract equations of general relativity or string theory feel alive, urgent, and deeply human. They provide a cultural vocabulary and a sense of wonder that can fuel decades of painstaking research. In some remarkable cases, fiction has even anticipated theory. The idea of a multiverse, a staple of comic books and sci-fi for decades, has evolved into a serious, if controversial, topic of cosmological debate. The holodeck from Star Trek prefigured discussions about virtual reality and the nature of simulated experiences. By dreaming boldly and without constraint, science fiction writers can sometimes map out the territory that scientists are only just beginning to approach, acting as unconscious scouts for the frontiers of knowledge. This rich cultural history does more than just bridge entertainment and education. It fundamentally humanizes the scientific pursuit. It reminds us that the drive to understand the cosmos is not a sterile, robotic process conducted in isolated labs. It is a deeply human story of curiosity, imagination, and the relentless desire to see beyond the horizon of the known. The same creative impulse that leads a novelist to envision a fourth spatial dimension leads a physicist to write an equation describing it. One uses the language of metaphor and narrative, the other the language of mathematics and logic, but both are explorers charting the same unknown territory. By embracing this shared heritage, we see that the quest to understand gravity's hidden origins is not just a technical problem to be solved, but a grand and ongoing story, one of the greatest narratives our species has ever told itself about the nature of reality and our place within its vast, multidimensional tapestry. So how do we take these extraordinary, almost unbelievable ideas and make them tangible for a student in a classroom or a curious viewer at home? The challenge of teaching multidimensional physics is as profound as the science itself, because we are essentially trying to describe a color that no one has ever seen using a language that was never designed for it. The key lies not in dumbing down the concepts, but in building robust conceptual bridges using analogies, models, and interactive experiences that allow the human mind to grasp the logic of a reality it cannot directly perceive. One of the most enduring and successful tools in this endeavor is the simple analogy. The rubber sheet model for spacetime curvature is a perfect example. We can't see the four-dimensional fabric of the universe warping, but we can all understand what happens when a heavy bowling ball is placed on a stretched trampoline. The marble rolling around the indentation doesn't know about the ball's mass, it just follows the curve. This simple demonstration translates the utterly abstract mathematics of general relativity into a physical, intuitive experience that anyone can understand and remember. It's a gateway, a first step that makes the deeper, more complex theory approachable. This work of translation is being pioneered by incredible institutions dedicated to public education. The Perimeter Institute for Theoretical Physics in Canada, for instance, isn't just a research center, it's a powerhouse of outreach. They produce beautifully animated videos, detailed explanatory articles, and teacher resources that break down the nuances of string theory, quantum gravity, and extra dimensions without sacrificing scientific rigor. Similarly, a vibrant community of science communicators on YouTube and other platforms has emerged as a vital educational force. Creators like PBS Spacetime, Veritasium, and Minutophysics use the power of animation and visual storytelling to construct mental models for their audiences. They might use the analogy of an ant on a hose to explain compactified dimensions, or sophisticated CGI to illustrate the journey through a Calabi-Yau manifold. These creators act as essential interpreters, transforming dense academic papers and esoteric mathematical concepts into engaging narratives that captivate millions, proving that there is a massive public appetite for deep science when it is presented with clarity and passion. But the most impactful learning often happens not through watching but through doing. This is where hands-on, interactive models become invaluable. Imagine a workshop where students don't just hear about higher dimensions but can physically manipulate them. Using virtual reality headsets, they could be immersed in a simulation where they can rotate a hypercube or a tesseract, watching as its strange geometry unfolds and refolds in ways that defy their three-dimensional intuition. Museums and science centers are increasingly developing exhibits that use light, sound, and touch to give visitors a visceral feel for these ideas. There might be a station where you can create a miniature black hole in a simulation and watch how it distorts light, or a collaborative game that demonstrates how quantum entanglement might work across a higher dimensional bulk. These experiences move learning from the passive to the active, forging neural pathways that a lecture alone could never build. This massive effort in education and outreach is far more than a nice addition to scientific research. It is a critical investment in our collective future. Public understanding fuels public support, and public support is what secures the funding for massive, long-term projects like the Large Hadron Collider or the next-generation gravitational wave observatories. When taxpayers understand that their investment is driving humanity's greatest intellectual adventure, they are far more likely to champion it. More importantly, demystifying these concepts is how we inspire the next generation of pioneers. A child who watches a video about warped extra dimensions or gets to play with a space-time curvature simulation in their physics class isn't just learning a fact. They are being invited on a grand adventure. That moment of wonder, that spark of, "I want to understand this," is where future Einsteins and Kip Thornes are born. It ensures a continuous pipeline of brilliant, curious minds ready to take up the challenge and push the boundaries even further. Ultimately, charting the forgotten dimensions of the universe cannot be the work of a few isolated geniuses in ivory towers. It is, and must be, a collective human endeavor, a conversation between researchers, educators, students, and the endlessly curious public, all working together to illuminate the deepest secrets of the cosmos. This incredible journey into the nature of reality reveals a beautiful truth. The deepest scientific discoveries rarely happen in isolation. The quest to understand gravity's hidden origins isn't just a project for physicists. It is a magnificent, collaborative symphony that brings together the most powerful tools of the human mind from across all disciplines. At its heart, this endeavor is a partnership between two ancient fields, mathematics and physics. mathematics provides the essential language and the rigorous tools, the differential geometry to describe curved, higher-dimensional spaces and the topology to classify their fundamental shapes. Physics, in turn, provides the motivation and the experimental crucible, asking the concrete questions about how particles behave and forces interact that demand these mathematical tools be developed and applied. This is not a one-way street. The abstract geometries explored by mathematicians a century ago, with no apparent application to the real world, are now the very blueprint string theorists use to model the compactified dimensions that might shape our universe. This synergy is perfectly illustrated by the ongoing, decades-long effort to classify all possible Calabi-Yau manifolds. This is a monumental task that involves teams of pure mathematicians working hand in hand with physicists, using abstract algebra and geometry to catalog the possible shapes of the hidden universe, each one representing a potential set of physical laws. The collaboration is so deep that it's often impossible to say where the mathematics ends and the physics begins. They have fused into a single, unified pursuit of truth. But the interdisciplinary web extends far beyond this core partnership. In recent decades, computer science has become an indispensable third collaborator. The complexity of the equations involved in string theory and the mind-boggling intricacy of the geometric shapes are so vast that they simply cannot be solved by hand. Supercomputers around the world now run sophisticated algorithms to simulate the behavior of strings in higher dimensions, to calculate the properties of predicted particles, and to help visualize the structures that our three-dimensional brains cannot intuitively picture. Machine learning is now being employed to sift through the millions of possible Calabi-Yau shapes, searching for patterns and correlations that might point to those that produce physics resembling our own universe. This is a classic example of cross-pollination. A problem in fundamental physics has driven the development of new computational techniques, and those techniques are now opening doors to discoveries that were previously mathematically intractable. Perhaps most surprisingly, even the field of electrical engineering is now contributing to this cosmic search through the development of metamaterials. These are artificially structured materials designed to manipulate electromagnetic waves in ways not found in nature. Engineers can now create invisibility cloaks that bend light around an object or materials that make an antenna behave as if it's a different shape. The mathematical equations that describe how light moves through these engineered materials are strikingly similar to the equations that describe how matter and energy warp spacetime in general relativity. This means that a researcher can now build a tabletop experiment using microwaves and a carefully constructed metamaterial to simulate the behavior of light near a black hole or even in a curved, higher dimensional space. It's a breathtaking example of how a practical engineering innovation can provide a tangible, experimental testbed for the most abstract theories of cosmology and gravity, creating a direct bridge between the workshop and the cosmos. This holistic view underscores a crucial point. Profound progress is born at the intersections of knowledge. The most transformative insights often occur when experts from different fields share their language, their tools, and their unique perspectives. The question of why gravity is so weak and whether it points to unseen dimensions is not just a puzzle for physicists to solve in isolation. It is a challenge that requires the abstract beauty of mathematics, the data-crunching power of computer science, and the ingenious application of engineering. It is a testament to the unity of knowledge, showing that our efforts to understand the farthest reaches of the cosmos are deeply and wonderfully connected to our drive to create new technologies and solve practical problems here on Earth. This collaborative spirit reminds us that the journey to map the hidden architecture of the universe is ultimately a collective human endeavor, drawing on the full spectrum of our creativity and intellect. While string theory and brane worlds offer compelling visions of a higher dimensional reality, they are not the final word. The quest to understand gravity's true nature is a living, breathing field of science, and several other innovative frameworks are emerging from the shadows, each proposing a radically different path to unification. One particularly intriguing idea is known as asymptotic safety. This approach suggests that we might not need extra dimensions, strings, or even a complete overhaul of physics to quantize gravity. Instead, it proposes that Einstein's general relativity could be made into a consistent quantum theory all on its own, if the strength of gravity evolves with energy in a very specific way. Imagine a river flowing towards a waterfall. That's a theory being pulled toward a fixed point or a singularity by its own renormalization group flow. Asymptotic safety posits that quantum gravity could be like a river that flows towards a waterfall, but then miraculously plateaus into a calm, predictable lake just at the edge. The theory becomes safe from the destructive infinities that usually plague quantum gravity calculations at high energies. In this scenario, gravity is fundamental and quantum, but it operates entirely within the familiar 4 dimensions of spacetime, rendering the need for extra dimensions unnecessary. It's a minimalist dream, suggesting the answer was hidden in plain sight within Einstein's equations all along, waiting for the right mathematical lens to reveal its quantum heart. Another paradigm-shifting concept completely inverts our understanding by proposing that gravity is not a fundamental force at all. This is the core of emergent gravity models, most famously championed by Dutch physicist Erik Verland. In his entropic gravity framework, gravity is not a force mediated by particles or a curvature of spacetime, but an entropic force, a side effect of the natural tendency for disorder to increase. Think about a simple everyday example. If you drop a dye capsule into a glass of water, the dye molecules will spontaneously spread out to maximize their entropy or disorder. Now apply this to the fabric of spacetime itself. Verland suggests that the information content of spacetime, described by holographic principles, has an inherent tendency to become more disordered. When you place a massive object like a planet into this system, it disrupts the entropy, and the natural response to regain maximum disorder manifests as an inward push, what we perceive as the attractive force of gravity. It's as if gravity is a thermodynamic illusion, much like the pressure of a gas is not a fundamental property, but emerges from the collective jostling of countless molecules. In this breathtaking view, the need for gravitons or extra dimensions vanishes. Gravity's apparent weakness isn't because it's leaking away, it's because it's a statistical effect, a cosmic consequence of information and entropy playing out on the largest possible scales. Looking even further beyond the horizon of current theory, we must consider the possibility of entirely new paradigms that we haven't yet conceived. The history of science is a graveyard of perfectly reasonable assumptions. For centuries, physicists were certain the universe was governed by Newtonian mechanics, until Einstein showed it was merely a low-energy approximation. We now operate under the assumption that quantum mechanics and general relativity are the ultimate descriptions, but what if they, too, are just facets of a deeper, more bizarre reality? The next great theory might not emerge from a gradual refinement of our current ideas, but from a conceptual rupture so profound it makes our current debates look quaint. It might be based on a new kind of mathematics not yet invented, or a principle that completely redefines our concepts of information, causality, or even time. Perhaps the universe is fundamentally computational, and the laws of physics are the output of a complex algorithm. Or maybe consciousness itself plays a role in shaping reality, idea that currently sits firmly in the realm of philosophy, but could one day find a rigorous mathematical expression. These may sound like wild speculations, but that is precisely the point. The most transformative breakthroughs often come from questioning the very foundations we consider unshakable. What unites these diverse future theories is their dynamic relationship with the concept of extra dimensions. For some, like asymptotic safety, dimensions are a fixed stage. For others, like entropic gravity, dimensions themselves might be an emergent property, a convenient way to describe the relationships between quantum bits of information. A future theory could even resurrect dimensions in a new form, perhaps proposing that they are not spatial in the way we understand, but something else entirely dynamic, fluctuating, or even conscious. The key takeaway is that science is not a march toward a single, predetermined destination. It is an ever-evolving conversation, a dynamic ecosystem of ideas where today's leading theories are tomorrow's historical footnotes, valuable stepping stones that paved the way for a deeper, more astonishing truth. This open-ended narrative is not a sign of weakness but the greatest strength of the scientific endeavor, a perpetual reminder that the universe is always more imaginative and mysterious than we can possibly imagine. But with the breathtaking potential of accessing new dimensions comes a profound and inescapable question of responsibility. The power to manipulate the very fabric of spacetime would be perhaps the most transformative capability humanity has ever stumbled upon, dwarfing even the discovery of nuclear fission. And as the famous adage reminds us, with great power comes great responsibility. The ethical implications of such a discovery are as vast and uncharted as the dimensions themselves. Imagine if we could tap into the energy of these higher dimensional realms. Theoretically, it could provide a near-limitless clean power source, solving our energy crises forever. Or consider the mind-bending possibility of dimensional travel, not just faster than light journeys across our universe, but shortcuts through the bulk to points unimaginably far away. This isn't just science fiction. It's a potential future that demands we think carefully about who controls this technology and how it is used. Would it become a tool for unification, bringing humanity together to explore the cosmos, or a weapon of unimaginable power, creating a geopolitical divide far greater than any nuclear arms race? The parallel to the development of nuclear physics is both instructive and sobering. The scientists of the Manhattan Project were driven by a fear that Nazi Germany would develop the atomic bomb first. In their race to unlock a fundamental secret of the universe, they succeeded, only to usher in an era of existential threat that hangs over our species to this day. The same intellectual curiosity that leads us to probe the origins of gravity could, if pursued without a parallel ethical framework, lead to consequences we can barely conceive. A weapon that could destabilize the compactified dimensions at a specific point, for instance, might not just destroy a city, but unravel the local fabric of spacetime itself. This isn't a call to halt scientific inquiry, but a powerful argument for integrating ethicists, philosophers, and policymakers into the conversation from the very beginning, not as an afterthought once the genie is already out of the bottle. This leads to an even deeper philosophical quandary, the concept of forbidden knowledge. If we were to discover that these extra dimensions are not empty voids but contain other forms of existence, perhaps even other intelligences, do we have the right to intrude? What if our probing, our attempts to access these realms, inadvertently causes harm or introduces instability into their reality? Conversely, what if we discover that these dimensions hold inherent dangers, exotic particles or forces that are inherently destructive to our form of matter? There is a compelling argument from some thinkers that certain doors, once opened, cannot be closed, and that some knowledge might come with a price tag too high for humanity to pay. The very act of charting these forgotten dimensions could be what makes them remembered, and therefore potentially dangerous. This isn't about fear-mongering. It's about exercising a humility that acknowledges that our thirst for understanding must be tempered by wisdom and a deep respect for the unknown. The only viable path forward, echoed by numerous scientists and ethicists, is one of radical international cooperation. The exploration of extra dimensions cannot be a national competition like the space race of the 20th century. The potential risks are global, and therefore the governance and oversight of this research must be global as well. We need to establish international treaties and regulatory bodies, akin to the International Atomic Energy Agency but far more robust before the technology is even within our grasp. This ensures that the incredible benefits, revolutionary energy, profound cosmological insights, perhaps even the salvation of our species, are shared by all of humanity, and that the existential risks are managed with the utmost caution and transparency. The journey into the multidimensional nature of reality is the greatest adventure we could ever undertake, but it is an adventure we must embark upon together, with our eyes wide open to both the wonders and the warnings that lie in the spaces between. It's easy to get swept up in the thrilling possibilities of higher dimensions, especially when pop culture so often portrays them as gateways to parallel worlds or instant teleportation. But between the exciting theories and the hard science, a fog of misunderstanding has settled, and it's time to clear the air. The most common misconception is that these extra dimensions are just like the three we know: vast, expansive realms we could theoretically walk through if we just found the right door. This image, popularized by everything from Stranger Things to Doctor Who, is a powerful narrative device, but it's a dramatic oversimplification of the physics at play. In reality, the extra dimensions proposed by string theory are not alternate universes you can visit. They are mathematical necessities with very specific and incredibly tiny physical properties. They are curled up and compactified at a scale so small that the concept of traveling into them is meaningless. You can't pilot a spaceship into a dimension that is smaller than an atom any more than you could drive a semi-truck through a keyhole. These dimensions are part of the fundamental geometry of space itself, woven into the fabric of every point around us, not a destination on a map. This leads directly to another pervasive myth, the idea that unlocking the secrets of extra dimensions would grant us godlike control over gravity, allowing for anti-gravity devices or instantaneous portals. While it's fun to imagine, this misunderstands the nature of the theory. The models that suggest gravity is leaking into other dimensions don't propose that we can plug the leak or redirect the flow. They describe a fundamental property of the gravitational force based on the geometry of the universe. Manipulating that would require manipulating the geometry of space itself on a cosmic scale, a feat that would demand energies comparable to those at the birth of the universe. It's not a matter of engineering, it's a matter of fundamental physical law. The same goes for dimensional portals. The concept of a wormhole, often used in science fiction as a tunnel through higher dimensions, is a valid solution to Einstein's equations, but stabilizing one and making it traversable would require a form of matter with negative energy density, something we have no evidence even exists in our universe. These are not technologies waiting to be invented. They are extreme hypothetical scenarios that push the limits of known physics. We also have to address the notion that because these ideas are strange and complex, they are no different from pure science fiction or, worse, pseudoscience. This is a critical distinction to make. The proposal of extra dimensions is not a wild guess. It is a rigorous mathematical consequence of attempting to reconcile quantum mechanics with general relativity. It makes specific, testable predictions, like the production of micro-black holes in colliders or deviations in the strength of gravity at minute scales. While these predictions haven't been confirmed yet, the scientific process is all about testing and falsifying ideas. This is the complete opposite of pseudoscience, which avoids testing and operates outside the peer-reviewed system. The value of science fiction, however, should not be dismissed in this process. A movie like Interstellar may take creative liberties with its depiction of a five-dimensional tesseract, but it also inspires a sense of wonder and curiosity that drives real scientific inquiry. The key is to appreciate the inspiration while recognizing the boundary between narrative spectacle and theoretical physics. Finally, there's a subtle but important misconception that the existence of extra dimensions would make our reality less real or significant. If we're just one brain in a vast bulk, does that diminish our place in the cosmos? Quite the opposite. This perspective doesn't reduce our reality, it expands it. Understanding that the force that guides the planets and shapes the galaxies might be a shadow of a deeper, richer cosmic architecture adds a profound layer of majesty to the universe. It suggests that there are layers of reality operating beyond our ordinary perception, and our ability to use mathematics and reason to potentially detect them is a testament to the power of the human mind. Debunking these myths isn't about shutting down imagination. It's about channeling that imagination toward a more accurate and truly awe-inspiring understanding of how the universe might actually work, ensuring our curiosity is guided by clarity and a respect for the scientific method. It's one thing to grapple with these concepts intellectually, to nod along with the mathematics and the theories, but it's something else entirely to let them sink in and truly change how you see the world right outside your window. We began this journey with a simple, almost heretical question. What if the gravity we feel every day is not fundamental? What if it's just a side effect, a faint echo rippling into our world from dimensions we can't perceive? If you allow that idea to settle, it can fundamentally reshape your daily perspective in the most beautiful and humbling ways. Consider the simple act of dropping your keys. You hear the jingle as they hit the table, a mundane event you've experienced 1,000 times. Newton explained the how with his laws, and Einstein explained the why with the curvature of spacetime. But now we're adding another, deeper layer. That gentle, inevitable pull towards the Earth isn't just a force or a curvature, it could be a whisper. A clue. It's a tangible piece of evidence pointing to a cosmic architecture of breathtaking complexity, a reality with hidden folds and dimensions operating just beneath the surface of our perception. The ordinary becomes extraordinary. The morning coffee cup that stays firmly on the desk, the rain that falls from the sky, even the very weight of your own body. These are no longer just facts of life. They are daily, personal interactions with a profound cosmic mystery. You are not just living your life, you are constantly engaging with the hidden mechanics of the universe. This realization cultivates a powerful sense of humility, a necessary counterbalance to the human tendency to believe we have everything figured out. For centuries, we thought we lived on a flat Earth at the center of creation. Then we learned we orbit an average star in a remote corner of a galaxy that is one of billions. Now we are confronted with the possibility that even the dimensions of space we take for granted are merely the visible part of a much larger, multidimensional reality. Acknowledging how much we don't know isn't an admission of failure, it's an invitation to a lifetime of wonder. It's the understanding that the universe is far stranger, more complex, and more magnificent than our current models can describe. This mindset is the very engine of curiosity and innovation. It's what drives a scientist to spend decades searching for a particle that may not exist, or an engineer to design an experiment to test a seemingly impossible idea. It's the feeling that there are still great discoveries to be made, that the next profound breakthrough is waiting just around the corner, hidden in the data from a collider or encoded in the ripple of a gravitational wave. Many of the physicists who work on these frontier ideas describe this perspective as genuinely transformative. They don't just see their research as a job, they experience the universe as a living, breathing puzzle of infinite depth. The late, great Richard Feynman often spoke of the awe he felt when contemplating a simple flower, seeing not just its color and shape, but the intricate molecular dance and cosmic processes that brought it into being. For a modern theoretical physicist, that awe is extended to the very fabric of space. They might look at the moon hanging in the night sky and not just see a celestial body held in orbit, but also ponder the gravitons that mediate that attraction, wondering how many of them are momentarily slipping away into a higher dimensional bulk, making the moon's pull just a tiny bit weaker than it otherwise would be. This isn't an abstract exercise, it's a way of seeing that makes the universe feel deeply interconnected, where the largest scales are intimately tied to the smallest, and where every moment is saturated with evidence of a reality we are only beginning to grasp. This shift in perspective is the ultimate gift of this exploration. It takes concepts that seem locked away in esoteric physics papers and brings them into the living room, making them relevant to anyone who has ever looked up at the stars and felt a sense of wonder. These ideas are not just for physicists. They are for anyone who wants to experience the world with a greater sense of mystery and possibility. They remind us that the greatest adventure is the one happening right here, right now, in the seemingly ordinary pull of gravity that holds our world together and connects us to the hidden dimensions of the cosmos. The quest to unravel the deepest secrets of the cosmos is a testament to one of humanity's greatest strengths, our ability to come together across borders, languages, and cultures in pursuit of a common goal. Researching something as profoundly abstract as extra dimensions isn't the work of a lone genius in an isolated lab. It is a massive, coordinated, and beautifully global endeavor. This collaborative spirit is embodied in places like CERN, the European Organization for Nuclear Research, which operates the Large Hadron Collider. But CERN is far more than a European project. It's a vibrant, international hub where over 10,000 scientists from more than 100 countries converge, bringing with them not just their expertise, but their unique perspectives, their diverse ways of thinking, and their shared passion for discovery. When particles collide in that 27-kilometer ring beneath the French-Swiss countryside, the data they produce is analyzed by a global brain trust. A theorist in India might work with an experimentalist in Brazil to interpret a signal, while an engineer from Japan and a programmer from South Africa collaborate on the next detector upgrade. This isn't just convenient, it's essential. A challenge this immense requires the collective intellect of our entire species. The varied approaches fostered by different educational systems and cultural backgrounds act as a powerful catalyst for innovation, ensuring that no blind spot goes unexplored and no potential solution is overlooked. This model of international cooperation extends far beyond particle colliders. Consider the future of gravitational wave astronomy with the Laser Interferometer Space Antenna, or LISA. This ambitious mission, led by the European Space Agency with crucial contributions from NASA and scientific institutions worldwide, will consist of 3 spacecraft flying in a precise triangular formation millions of kilometers apart, connected by lasers. Their goal is to detect the low-frequency rumble of supermassive black hole mergers, sounds that are utterly inaudible to Earth-bound observatories like LIGO. The technological marvel of LISA is only possible because of shared resources and expertise. No single nation bears the colossal financial burden or possesses all the necessary engineering genius alone. From the delicate thrusters needed for flawless formation flying to the sophisticated algorithms that will filter cosmic noise from the signal, every component is a product of global partnership. This mission and others like it are physical proof that when faced with a mystery as grand as the nature of spacetime itself, our national boundaries dissolve, replaced by a shared identity as explorers. The driving forces behind this research read like a United Nations of science. Institutions like the Perimeter Institute for Theoretical Physics in Canada serve as global gathering points, hosting conferences and workshops that connect minds from every continent. In the United States, the National Science Foundation provides grants that support researchers at universities across the country and fund their international collaborations. Japan's Keikei Particle Physics Laboratory and its Super Kamiok and neutrino detector are critical nodes in the global network. These projects are so astronomically expensive and technologically demanding that they simply cannot be built or operated by one country. They are monuments to our collective curiosity, paid for and utilized by a planetary community. This collaborative framework does more than just pool money and brainpower. It builds a resilient and enduring scientific culture. It creates a web of personal relationships and mutual respect that transcends political tensions, ensuring that the pursuit of knowledge continues steadily, a constant thread of cooperation, even when other dialogues between nations break down. By uniting in the face of the unknown, we don't just increase our chances of success, we affirm a fundamental truth about humanity, that our desire to understand the universe is a unifying force, one that reminds us we are all on this same small planet, gazing up at the same stars and wondering together what other realities might lie just beyond our current perception. This monumental challenge of finding needles in cosmic haystacks is precisely where a revolutionary new partner enters the search: artificial intelligence. While our human minds are brilliantly creative, we are simply outmatched by the sheer volume and complexity of data generated by modern experiments and the labyrinthine mathematics of higher dimensional theories. This is where AI and big data analytics are fundamentally transforming the hunt, shifting the quest for forgotten dimensions from a purely theoretical pursuit into an increasingly empirical data-driven science. Imagine the task of finding a single unusual signature among the billions of particle collisions inside the Large Hadron Collider. Each collision is a firework of data, a chaotic spray of particles that physicists must meticulously reconstruct. Hidden within that unimaginable torrent of information could be the faint, telltale sign of a graviton briefly dipping into an extra dimension, registered as a tiny amount of missing energy. For human researchers, this is like listening to a crowded stadium and trying to pick out a single, unique whisper. Machine learning algorithms, however, are perfectly suited for this. They can be trained on simulated data to recognize the standard patterns of known physics and then flag the rare, anomalous events that deviate from the norm. These AI systems don't get tired, they don't suffer from confirmation bias, and they can process datasets of a size that would take a human team millennia to review. They act as incredibly sensitive digital filters, sifting through the noise of ordinary physics to hopefully isolate the signal of something extraordinary, dramatically accelerating the pace of discovery. Beyond analyzing experimental data, artificial intelligence is also tackling one of the most daunting theoretical problems: classifying the possible shapes of the hidden dimensions themselves. In string theory, the specific geometry of the compactified Calabi-Yau manifolds determines everything about the physics of our universe, the particles, the forces, everything. The problem is, the number of possible Calabi-Yau shapes is astronomically vast, estimated to be in the hundreds of millions or even more. For a human mathematician, classifying even one of these intricate, multi-dimensional shapes is a career-defining task. To map the entire landscape by hand would be utterly impossible. This is where neural networks are stepping in as indispensable collaborators. Researchers are now training AI systems to analyze the mathematical properties of these manifolds, to recognize patterns and correlations between their geometry and the resulting physical laws they would produce. In a landmark project, physicists used AI to study a specific set of complex Calabi-Yau shapes, a task that would have taken decades using traditional methods. The neural network completed the analysis in a matter of hours, not only verifying known results but also discovering new, unexpected relationships between the shapes. This isn't about replacing mathematicians. It's about augmenting human intuition with machine-scale processing power, allowing us to navigate a mathematical universe of possibilities that was previously too vast and complex to ever explore. This synergy between human creativity and artificial intelligence is perhaps our most powerful tool yet. We are moving beyond simply using computers as fast calculators. We are building systems that can learn, hypothesize, and even guide the direction of research. For instance, AI can run through millions of simulations of how gravity might behave in different dimensional configurations, comparing the results against real-world observations to identify which models are most plausible. It can take the null results from experiments, the times we didn't find anything, and use them to rule out entire families of theories, helping to narrow the search with an efficiency that was previously unimaginable. This transforms the scientific process. The charting of forgotten dimensions is no longer a solitary theoretical endeavor. It is becoming a collaborative dialogue between human minds and machine intelligence, each playing to their strength. We provide the deep questions, the physical intuition, and the creative leaps. The AI provides the brute force data crunching, the pattern recognition at a scale we cannot match, and the ability to manage complexity that would overwhelm any individual. Together, we are building a new kind of scientific instrument, one that extends our intellect into realms of data and mathematics we could never hope to navigate alone, bringing the abstract dream of discovering new dimensions closer to a tangible, empirical reality than ever before. Imagine being the person who finally cracks a mystery that has puzzled the greatest minds for centuries. The question of gravity's true nature and the existence of hidden dimensions isn't just an academic exercise for established physicists. It is a wide-open frontier, a siren's call to the next generation of scientists, engineers, and dreamers. This is where the next great leaps in human understanding will be made, and the people who will make them are likely in a classroom right now, their curiosity just waiting to be ignited by an idea this profound. For a young person with a passion for how the universe works, there is no more thrilling field to enter. This is the cutting edge, a domain brimming with puzzles that could easily lead to Nobel Prize-winning discoveries. The foundational work is laid, but the monumental tasks of finding experimental evidence, refining the mathematics, and perhaps even building the technology to test these ideas are all still ahead. This isn't a field with all the answers. It's a field where the biggest questions are still up for grabs, offering a lifetime of exploration and the potential for a legacy that literally changes reality as we know it. We see this spark of inspiration catch fire all the time. There are countless stories of students who attended a public lecture on string theory or watched a documentary about the hunt for extra dimensions, and found their life's calling in that single moment. A high school student might be struggling with calculus until they learn that those same equations can describe the curvature of a higher dimensional space, and suddenly, the math transforms from an abstract requirement into a powerful tool for cosmic discovery. University undergraduates are getting involved in this research earlier than ever, with programs at institutes like the Perimeter Institute for Theoretical Physics offering summer schools and research opportunities that allow them to work alongside leading experts. These programs don't just teach facts, they immerse young minds in the process of science, the collaboration, the dead ends, the exhilarating moments of insight. They show that science is a living, breathing, and deeply human adventure. The impact of this goes far beyond individual careers. Solving the mystery of gravity could unlock technological revolutions we can scarcely imagine today. Every time humanity has unraveled a fundamental force of nature, it has led to a transformation of our world. Understanding electromagnetism gave us the power grid, global communication, and every electronic device we use. Harnessing the strong nuclear force gave us new medical treatments and, contentiously, new sources of energy. If we can truly understand gravity at its most fundamental level, if we can learn whether it's leaking from other dimensions or emerging from quantum information, what doors might that open? The possibilities are the stuff of science fiction, but they are rooted in real scientific pursuit. We might discover new principles for energy generation that are completely clean and sustainable. We might develop entirely new forms of computation that use the properties of spacetime itself, or we might invent methods of propulsion that allow us to travel between the stars not by burning fuel, but by manipulating the gravitational fabric of the universe. These aren't guaranteed outcomes, but they are potential destinations on a map we are only just beginning to draw. This is why nurturing this curiosity is not a niche concern but a vital investment in our collective future. The journey to chart these forgotten dimensions will require more than just physicists. It will need brilliant engineers to design the next generation of particle colliders and gravity wave detectors. It will need computer scientists to write the algorithms and manage the oceans of data. It will need mathematicians to develop new tools for describing geometries we can't yet visualize. This quest is a beacon calling to a diverse array of talents and minds, uniting them in the greatest detective story of all time. By sharing these ideas with passion and clarity, we ensure that the pipeline of innovation remains full, that the conversation continues, and that the flame of curiosity is passed on. The students of today will be the ones who finally step into the cave that Plato described, not as prisoners, but as explorers, turning around to see the light of a deeper reality for the very first time, and returning to tell the rest of us what they found. And so, our journey through the hidden architecture of the cosmos brings us to a profound and humbling realization. The force that grounds us, that guides the planets and sculpts the galaxies, may be the universe's greatest whisper, a subtle clue pointing to realities beyond our ordinary perception. We've seen how gravity's astonishing weakness, a puzzle that vexed even Einstein, could be its most important feature, not a flaw. It could be the telltale sign that this force is not confined to our world but is spilling into and diluted by unseen dimensions curled up at every point in space or stretched across a vast higher dimensional bulk. From the elegant mathematics of string theory and its requirement for extra dimensions, to the mind-bending vision of brane worlds where our entire universe is a membrane floating in a grander reality, we have frameworks that transform this from wild speculation into rigorous, testable science. These are not just abstract ideas, they are being pursued with relentless ingenuity at places like the Large Hadron Collider, hunting for missing energy, and in delicate tabletop experiments measuring gravity's pull at distances smaller than a hair's width. While the evidence remains elusive, the very act of searching refines our questions and draws the map of the unknown with ever greater clarity. This quest does more than just push the boundaries of physics. It weaves together a tapestry of human endeavor, connecting the historical insights of Newton and Einstein with the philosophical ponderings of Plato, and driving the technological marvels of our most powerful machines. It reveals a universe that is far stranger, more complex, and more wondrous than we often assume in our daily lives. The journey to chart these forgotten dimensions is far from over. It will require our best creativity, our most courageous collaboration, and an unwavering faith in our ability to understand the cosmos. It is a reminder that the greatest discoveries often begin not with an answer, but with a question, a willingness to look at something as familiar as gravity and dare to ask, what if? As the legendary astronomer Carl Sagan once said, somewhere, something incredible is waiting to be known. That something might be hiding in the next set of data from a collider, in the precise tremor of a laser measuring spacetime, or in the equations on a theorist's chalkboard. It's waiting for the next curious mind to join the search. If this exploration has sparked your curiosity, make sure to subscribe and hit the bell for more deep dives into the mysteries of the universe. Let us know in the comments what part of this incredible idea resonated most with you. Thank you for watching and never stop wondering.